Let's start with a quick peek. Select top 5 asterisk from sales.customers. That's just the beginning. By the end of this course, you will be writing query like this at scale, analyzing data and optimizing performance like a pro. SQL stands for Structured Query Language. It was developed in the 1970s, yet it's still the backbone of most data analytics workflows today. SQL is declarative. You describe what you want, and the database decides how to get it. That makes queries powerful, reliable, and scalable, something you can't always do in Excel alone. Relational databases organize data in tables with rows and columns, kind of like Excel sheets, but much more robust. They let you store huge volumes of structured data, maintaining data integrity, allow multiple analysts to work at the same time, and provide fine-grained security. You might have heard of NoSQL databases, key value stores, document databases, and others. While NoSQL is great for certain applications, analytics almost always relies on SQL. Why? Because we need joins, aggregations, and reproducible queries, things relational databases excel at. In this course, we will focus entirely on SQL for relational databases. SQL is everywhere in data workflows. Analysts, data engineers, database administrators, software developers, and even data scientists rely on it. If you're in analytics or aspiring to get there, this course is built for you. Here's what we'll cover from start to finish. Selecting, filtering, and ordering data. Aggregation, group by, and conditional results. Joins and set operations. Data types and conversions. Functions, math, string, and date time. Subqueries and common table expressions, CTEs. Modifying data. Insert, update, delete. Database design, tables, and constraints. Views, temporary tables, and procedural control. Stored procedures, triggers, and transactions. Performance, statistics, execution plans, and indexing. Each chapter is structured so you can follow along, pause, practice, or skip ahead using the timestamps. To make this course even more practical, you can download the PowerPoint it's based on. It includes all the queries we'll cover, plus exercises for you to try on your own. Pause, run the queries, experiment, and come back. Links are in the description. The queries are in the speaker notes. We'll also be using Microsoft SQL Server Management Studio, which you can download for free. If you don't have a SQL Server installed yet, you can download a free developer edition along with the demo database we'll use. All the links are in the description. You don't need to worry about installation here. We focus entirely on querying and analyzing the data. With that out of the way, let's start simple. Chapter 1 begins with select statements, how to get your data, add conditional logic, and sort it. From there, we'll build step by step toward advanced analytics and performance tuning. If you already know what SQL is, feel free to skip ahead using the chapters. Otherwise, let's start at the very beginning and explore how analysts interact with databases. All right, here I am inside the Microsoft SQL Server Management Studio. Also, I have already downloaded and connected the Wide World Importers database. That's a demo database provided by Microsoft. With that out of the way, let's start writing our first select statement. When we select something, we start with select, and then, for example, with the small hyphen here, I can start a string data, and I can say hello world as header, for example, and then I could add another column, which means maybe a 1, which is then not in the hyphens, and this indicates that's a number. And let's call this column, this is a number. And that's already what I need. I can already run this. And then down here we see the result. We have named our columns as header, and this is a number. We have those columns in here. And then we have one row, and this contains hello world and a 1. Now I had simply hard-coded the values that I am querying. This is obviously most of the time not what we want. We want to get data out of our database. So let's have a look what tables we can work with. Here inside the Wide World Importers database, there are tables. And there are quite a bunch of tables. And as a simple example, I want to query now the sales.orders. So let's write another query. I can simply continue here to write the next one. Select, and now a special character asterisk, which means all columns that are available. Now we need to specify the table that I want to select from. It's from in the wide world importers database. I can with tabulator just follow the recommendations here for autocomplete. Dot, and now it's in the sales schema. Dot orders, in the orders table of the sales schema in the wide world importers database. Now when I mark this, I can individual mark it and say execute this query. Now we have here our first query that queried data from the database. But now let's say I don't want to see all those columns. I want to individually identify the columns that I'm interested in. And then in this case, I would remove the asterisk here and say, for example, I'm only interested in the order ID and in the order date. So which order came in on which date. Again, I mark it and I could hit execute again, or on my keyboard, F5 is the shortcut. And there we have the result of all 73,595 rows. I can scroll through them all here if I wanted to. All right, let's say I don't want to see all the rows all the time. I'm maybe just interested in the first 100 rows. Then I could simply go ahead and add here a top 100 after select directly following. And I can also run this query. And now we see, okay, now I only get the top 100 rows. Another option that I do have is to say, okay, I'm not interested in the top 100 number of rows, but the top 10 maybe % of rows. Running this will give me then 7,360 rows. Now let's have a look how we can sort our results. So I will remove the top 10% and I will add an order by order ID. This will not change much now as it is already ordered in the order ID, but this is how we order our results. As you see, we did not specify the order direction. By default, it's ordering in ascending order. That would be ASC. If I run this, that would not change the result. But I can change the direction in DESC for descending. If I run this now, we see that the highest number is on top and then the ordering goes down. This is how we order data. As you saw before, I can use the S keyword to name the column headers. So for now they are called order ID, but maybe let's say we want to name them order number. That's totally possible. Now the column is called order number. And this so-called alias can also be used in the order by clause. So after I've renamed the column up here, I can also use the new name down here. It works just as well. We can also order by multiple columns. For that, let me add another column over here. And let's say we are also interested in the customer ID. And then I could directly go ahead and say, okay, let's also order by the customer ID ascending. And one order number is always unique per row. So let's, instead of ordering by the order date, let's order in ascending order, first the order date and then the customer ID. Let's have a look at the result. So now we have the smallest order date in here. And if I go down, we see, okay, more and more data comes in, always later. And then the second ordering is by customer ID. So within each day, the customer ID is also ascending. As you can see, it goes up and up and up until we hit the next day where it starts from the beginning again, ordered by 2 columns. For the sake of completeness, I want to show you that you can also go ahead and write it quicker. You can say order by 1, 2. What it does now is first it orders by the first column that we have in here, which is the order ID, and then by the second one, which is the order date. It works perfectly fine, but I recommend to not get used to using this functionality because the problem is once somebody else takes up your query and reorders them, let's say we put the custom ID on the second spot, it will still work, but the result is different now. Now we ordered by the custom ID in the second place instead of the order date. So know what this functionality is if you see that somewhere, but I recommend not using it. Next up is our distinct keyword. For that, let me first pull another column, our salesperson person ID, and remove the order. If we run this, we see we have salespersons with ID 2, 3, 6, 7, and 8, and so on. But let's say we want a list of distinct values of the salesperson person ID. So we want to see each one only once. And this is exactly what the distinct keyword provides us with. If I run this, I can see, okay, we have exactly 10 salespersons with those IDs. We can also add multiple columns here, and they will then be distincted in combination. So we will now see the list of salespersons and their customers. If I execute this, and then as we saw before, let's add an order by here so it's a little more clean. Now we see a list of the customers of first the salesperson, person ID 2. And when I scroll down, we see the list of the customers of the salesperson, person ID 3, and so on. That's the distinct keyword. All right, but now you might be asking, okay, now I know that this person is number 3, but who is it actually? And we can see this in a different table. We have our table. There's a table application.people, which we might query. So let's say, for example, select star from application.people, where person ID equals to 3, because this is in this database, the person ID. Let's run this. And then we see, okay, this is Hudson Onslow. Now I don't want to always query this second table, but rather have it in here when I query my orders. So what can we do? Let's rewrite this. I can always restructure it with line feeds. And now we will be adding some conditional logic here. This is done by the case when statement. Case when salesperson person ID is equal to 3. So this is exactly the number that we have for the person here. Then what happens? Then let's say we return the string Hudson Onslow. Otherwise, let's say this was sold by someone else. And then we need to end this case when statement. And then I always like to put a little indentation here so we can see it's structured. And let's give this an alias and we call this our salesperson. Now I can run this whole thing. And we see, okay, the first one starts with sold by someone else. And then when I scroll down, here comes the part where Hudson Onslow is the seller. But now I also want to see who was the salesperson 2 in my query. And to do that, we could go ahead and nest our case when statements. Let's say in the else case, if it's not Hudson Onslow, then we can add another case when. Case when salesperson person ID equals to 2. Then, and I know it now because I looked up in the database before, but we could do it on the fly as well, but it's not needed. I know that one is Kayla Woodcock. And then again, we have another else here. And we will say, if it's neither Hudson Onslow, no Kayla Woodcock, it would be someone else. And then we need to end also this one. So we have 2 times we have opened the case when, and then we need to end it also 2 times. Running this, we see, okay, the first salesperson with the person ID 2 is Kayla Woodcock. If I scroll down now, then comes Hudson Onslow, and then the rest is sold by someone else. Theoretically, I could go ahead and make this exercise for all the salespersons, but later we will see in a more elegant way when we come to the joins. But for now, this is what we can do with the conditional case when logic. Now let's have a look how filtering our data with the where clause works. The keyword is where, which always indicates now we want to remove some rows from the final result set. Where is evaluated for every row in our data set. It is placed between the from and the order by statement. And we can also put case when statements inside of the where clause, which is something in practice you would see quite often. All right, let's just say we have a table that looks like this. We have salesperson, person ID, and in another column, order ID. Now we would run the following select statement. We select the order ID column from the sales.orders table, which is, let's say, this table that we see here. And then we add an where salesperson person ID equals to 2. So what happens is that for every row, we identify one by one the rows where we find the salesperson person ID 2. And only those columns will then be visible in the final result set. As you can see here, we have the order IDs 2, 4, and 6 left. All right, then let's see it in practice. So let's first clean up a little bit here so we have a clean sheet to work with our where condition. And as a reminder, when I run this, I get my 73,000 and something rows. Let's go ahead and add a where clause. And we say salesperson person ID shall be the 2. So we only want to see the rows where the salesperson person ID is equal to 2. And we run this, and that's exactly what we get. After the where clause, we add the order by statement if we wanted to. So let's just do that. We can also order this by the customer ID. Now we have the salesperson person ID and the orders by customer and so on. Now, just for the sake of completeness, it does not make much sense content-wise right now, but we do have the option to add also the case when statement here. Let's say case when salesperson person ID is 2, then hit, else no hit, and now I need to make it a condition here, because in the where clause we always need conditions. Something is true in the end or false, so to see if we shall see the row or not. So in this case I would say equals to, let's say, hit. So only the ones that are a hit for salesperson person ID 2 will be shown. Running this, we see this, and I could turn this around saying no hit. And now I will only see the ones that are not salesperson person ID 2. A more elegant way to get this result, if I wanted to get a no hit for all the rows that are not salesperson person ID, is I could remove all this and say, instead of equal, I could say unequal to 2. Now I will get the same result. All the salespersons that are not number 2. If I scroll down here, we can see there's no 2 in here. Let's say I also have the order date here as a column. And then I could also filter by the order date. Let's say the order date is bigger than or equal. That's also possible, bigger or equal to. And now I need to add a date here. And then I can say 2016 01 01. So 1st of January 2016. Running this, I will see only order dates after the 1st of January or including it. So now we saw how to filter on numbers and on dates. And the same thing we can do also, we can compare the string values. For that, let's go to the table where we have the names of the people. Select full name from application.people, as you remember, and there we have the full names. Running this, I could also filter this now, where full name is bigger or equal to, let's say, Kayla Woodcock. Now, ordered by alphabet, we can only see the ones that are bigger. So it exactly starts with Scalar Woodcock and then so on, KL and so on in the alphabet. If I would not say bigger or equal, but just bigger, then the first row will be gone and we will start with Kirsty Mihailov. That's exactly what happens then. Yep. And the operators that we do have available are greater or equal, less than or equal, or unequal. The next thing we might be interested in is filtering out only orders for a specific salesperson after a specific date. Then we need to combine two conditions. So first condition would be, for example, salesperson person ID is equal to 2. And the second one would be order date, bigger or equal to 2016 and so on. If I try to run this, it would not work because we need to combine those two conditions. This is, for example, where we can say and. Now we have a filter for the rows where both conditions need to be met because we combine them with and. Let's run this. And we see that this works. We only have the salesperson person ID 2 in here, and the order date is always after 2016. Perfect. Now, if we replace this and with an or, we are effectively saying, give me all orders that were either done by salesperson person ID 2 or are after this date. If I run this, we see, okay, first we see all the orders from salesperson person ID 2, but then we get mixed in here other salespersons, but only if the date is after the specified point in time. Now let's say we have a more complicated combination. We want to see all the salesperson person IDs 2 or 3, but only if the order date is after 2016. If we would go ahead and write salesperson person ID equals to 3 and order date is bigger than this, this would not give us a result that we want. Let's see. We see now rows for salesperson person ID 2 which are before 2016. Why does it happen? Because the and is a stronger bond, so to say. So this becomes one condition and this alone. So let's scroll down. For number 3, we would expect only after 2016. It's a little bit mixed. Let's order this result by salesperson person ID. Run this again. Scroll down to the number 3 and he's down here. And there you can see, okay, there it worked. Only 2016. One thing we could do now is say and order date is bigger or equal to 2016 also for the first salesperson. Then we see, okay, this would work. Another more elegant way we could do is instead of putting this twice in here, we can say we added parentheses around the salespersons. So it would read more like this. This is now one condition, and to this one condition, we add this condition. Running this, we also get the result we want. Salesperson, person ID 2 or 3, but only if the order date is after 2016. That's what we use the parentheses for, so we can override the standard combination logic. In technical terms, with the parentheses, we can override the order of precedence between the or and the and statements. Now let's come back to this filtering for the names. Instead of filtering by alphabet, let's say we only want results which start with a KA at the beginning. And this is where we can use the like keyword. This is special only for string columns. So full name is like KA. This will not return anything for now. But if we add a percentage sign here, running this, we get all the records that start with KA, but nothing else. If I scroll down here, that's an exhaustive list, nothing else. So what does it do? The percentage says anything may follow. So in this case, this like statement reads, give me everything that starts with KA, and then anything may follow, what still holds true for this condition. But we are also free to put the percentage sign wherever we want. So we could say, give me everything that starts with whatever, but ends with KA. Let's see this. Aha, now we have only Margita Kopeka, which ends with KA, and another person with the last name Kopeka. Also, we could put it in the middle here. So we can say, give me all the results that start with a K and end with an A, but in between you have a random number of characters. There we have the result. That is a percentage sign. Another special character we can use with the like is the underscore. The underscore means there's exactly one character, but not a random number of characters. So if we run, for example, this query, we get results that start with a K, then it's followed by exactly one character, and then on the third position we have another A, and then followed by a random number of characters. So we can see, okay, we have a K, then something in here, and then the third one is an A. Or with Clara, we have a K, and then the L is the part where we have the underscore, and then we have an A, and then followed by something else. This is the underscore filter. Another thing that we can do is put them in hard brackets, some characters. Let's say now we want ABC percentage. What might this do? Now it gets quite complicated, I know. This means we want to have a text that starts with A, B, or C, and then it's followed by anything. Let's run this. Then we see a lot starting with A, and then some start with B, and some start with C. This is how we can filter by a list of specific characters. The same result we can also get if we add a dash in here, which means by alphabet, everything that's from A to C. And so in this case, it's the same result, right? A, B, C. If I scroll down here, we will also see the B again. Perfect. Another thing that we can do is we can negate this result with this little character. Now we get the result, everything that's not starting with ABC. Let's run this. And there you see it. It's D, E, and so on. All right, this is how to filter strings with the like keyword. Now let's have a look at another example on the orders table. What we were seeing before is that the order date filter bigger or equal to 2016. And let's say we can combine this, as you would have probably guessed, with another filter. Smaller or equal to, let's say, mid of that year, until 30th of June of that year. Works perfectly fine. As you see, nothing bigger than 30th of January 2016. But we can write this more elegant with the between statement. So we can say order date between, now we don't need this anymore, and this date. So now we get everything that is between 1st of January of 2016 and 30th of June of 2016. This gives us the same result, but it's just a little more elegant to write it like this. So you can immediately see that we filter one column on two conditions. One thing to keep in mind when you're using the between, it's always the inclusive filter. So this would be equal to this condition, bigger or equal and smaller or equal. That's the same result. But it's not, for example, this one, bigger or smaller without the equal part. Then we have a different result. And for this one, we cannot use the between. The last thing I want to show you in this chapter is the null value. So for that, I will get some other data in here, a column where we have null in there, picked up by person ID from void word importers dot sales.orders. Let's see what we are dealing here with. We have a null in here. A null means there's a missing value. It's unknown. If I scroll down a bit, there are some orders who are already picked. So business meaning would be the orders down here are already picked by a person, and these one are probably new orders where they are not yet picked. So it's unknown by which person they will be picked, probably in the future or not. Let's say we only want those orders that are not yet picked by a person. You might think you would just say where picked by person ID equals to null. But null is not a real value. It means just unknown. So you cannot compare unknown to unknown. That's just an SQL thing. If I execute this, I will get no results. What I need to specify is, instead of saying the picked by person ID is equal to null, because unknown cannot be equal to unknown, but we can say it is unknown, which means there's another special keyword is. So where picked by person ID is null. And that's working then. Now I get only the records where it is null. Now let's say we want all the orders that were not picked by person ID too. You might expect in here to also get the nulls, but you don't. That's again the same. We cannot compare null with a value. So if you wanted to get all the orders that were not picked by person ID 2 and they shall not be null, you would have to specify it as or picked by person ID is null. That's a common trap and something to always need to worry about when working with null. You always need to compare is null. So now we get them. And here we get the 3, 4, 5, 6 and so on, but the number 2 is missing. So this is how you filter inequality when you have a column combined with a null value. Except for filtering out null values, another option would be to handle it in a specific way as we want. Let's say we select case when picked up by person ID is null, then we can do something with it now. Let's say we will put in a -1. Otherwise, we will leave it as picked by person ID. And this is our picked by person. Running this. Now we have explicitly replaced the null values in here. Potentially we would want to show something more user-friendly, like unknown in here, but as picked by person ID is a number column, we cannot mix numbers and columns. In here, to do that, we would need to convert this column first to a string, which we will cover in a later chapter. So let's switch this to the email address, maybe. Email address. And then we would want to have this from the people table and do the same in here. And here we could then say unknown, as email address is already a string. And we have unknown emails in here. Perfect. Much shorter. As handling null values in SQL is the thing that you do very often. There are more comfortable functions for this. One example would be the isNull function. IsNull email address, and if it is null, replace it with the second parameter in here. Let's say unknown. And then we can get rid of all the rest here. Running this, we see the same. Pay close attention. This isNull, when we use it as a function, is one word. Before, when we were asking it as a condition, is null, there's always a space between. So that's a small little important differentiation here, but you can already see that this is differently colored from the SQL Server Management Studio. Besides is null, there's also a coalesce function, which does more or less the same. If we run this, we see the same result. The small little difference between is null and coalesce is that coalesce can take multiple arguments in here. And then it will return the first one that is not null. So we could put an email address here and then full name and then unknown. Does not make much sense, but that is how coalesce works. Now, instead of the null, we see here data conversion only, because this is what in the full name column. This does not work with the isNull function. This null does only take 2 arguments. Another difference between the two of them would be the following. isNull ABC. Now I'm writing a query directly without querying any table. 1 in contrast to coalesce. Running this, we see we have errors. If we run only the first one, it works, but the coalesce version does not work, as it's failing to convert an ABC into a number. So in this case, we would need to convert the number to a string, which we will see in a later chapter how to do that. So now you might come to the conclusion that isNull is superior to coalesce, but let me show you the following. I paste in here a query that is taking the phone number and the user preferences. And when I run this query, now we see a lot of data. But what I wanted to show you is, first of all, we set the phone number and then the user preferences. The content is not important right now, but see that the phone number is rather short and this user preference is a very long JSON string. It goes on and on and on. And if we put in the phone number first and then the user preferences, then we generate a column with isNull, the isNull cropped column. And here you can see the problem. It's really cropped. It's stopping here. So what isNull does is it takes the length from the first column and applies it to all the other values that are coming here from the second parameter. So we lose all the data over here. Coalesce, on the other hand, is retrieving the full data also from the second column. So my recommendation is to use coalesce most of the time, unless you really need the isNull functionality, but coalesce is a safer bet. Now let's revisit the where conditions again. There's a where in parameter that I want to show you right now. The following query is something that you should now be able to understand. We do a distinct of order ID from sales orders, and the order ID shall be 1, 3, or 5. Running this, we get 1, 3, 5. If you had more in here and you wanted to have a long list of things that you want to filter for, it would get quite long. And that's where the in operator comes into play. We can say order ID in 1, 3, 5, and then we can get rid of the rest. So it does exactly the same, but it's much shorter. In here, we do have values. And as you know, null is not a value. So if I would go ahead and try something like this, it works, but I don't get any records with null. So could be that there are no values with null, but to be really sure, we would have to write the following. Or order ID is null, like as we had it before. Now running this, we see the same result, but now it is safe. And we explicitly said, okay, we also want null values if there are any in our table. Otherwise, the first version would not have retrieved us the null. Like this does not work. All right, so you remember when we wanted to negate our result, we could say something like this, right? Not equal to 1. And then if I would also want to exclude the 2, I would say order ID unequal to, or let's keep our example, the 3. And then we run this, we get our results. Now, if I wanted to do the same with the list again, like 1, 3, 5, I could not really do this with the in, right? In, and then, yeah, something like this you could imagine, but no, that's not going to work. So we need to get rid of this again, but we have a negation. And simple enough, it's the not. So not order ID in. So this not will always negate things that evaluate to a true or false value. Executing this, we see, works just fine. In practice, very often you will encounter the following. Order ID is not null. And like this, we can easily filter out the null values if we are not interested in them. With SQL, you can also do some arithmetic operations. Let me paste in some queries here, which we will go through. Select 5 plus 3 is something we can execute, which gives us an 8. We have the minus 5. Minus 2 is 3. We have the multiplication 5 times 2. Then we have the division, which gives us the full integer back. And as you can see, we only get back a 2, which is because here we are calculating with full integers. Only full integers are returned. It's not the 2.5. If we want the 2.5, we need to switch our first value to a decimal place number representation. Running this, we will get the 2.5 and some precision zeros behind it. Then there's also the modulo operator, which returns the rest of division operations. And here we have the 1. We can also do additions on strings, hello plus world with a space in between, results to hello world. And we have some order of precedence in here. If we do plus and multiplication, first the multiplication and then we add another 2 to it. And we can override it with parentheses. Now first plus 2 and then the result times 5. This was not yet very spectacular, but let me paste in another query. And in here we calculate based on the values retrieved from columns from real tables. So in this case, unit price times quantity is our sales. Let me run this. And then we see we have here an order with an order line ID and some unit price and the quantity. And here we calculate our sales based on the product of 230 times the quantity of 10. With group by, we group together rows of the same value. And syntax-wise, it follows after the where clause, and it is also technically where it happens. First, we filter the rows that we don't want, and then of this filtered set, we do the group by aggregation. Columns that are not specified in the group by are not used for the grouping. On those individual groups, we can then calculate aggregations. For example, count the number of rows within each group. When we use group by, all columns need to be either be grouped by or used in the aggregation only. We cannot add loose columns when we use group by. When we run a group by query, the following thing happens. Let's say we have the following table with two columns, salesperson, person ID, and the order ID. And we run a group by query, which shall count the order ID over all salesperson IDs. Then per each group, then first the rows will be put into groups for, in this case, salesperson ID. So first of all, we have a group for the ID 1, and then for all the ID 2s, and then the one with the ID 3. For each of these groups, we will then count the order IDs. So we have 2 order IDs in the first group, 3 in the second group, and 1 in the third group. Running this query on the whole dataset, we come up with the salesperson person ID and the number of their sales. So as you can see, they all have pretty much the same number of sales. And then if we wanted to rank over all our salespersons by the number of sales, we could reuse the name that we gave over here and run it. And now we have a column ordered by the sales, and we see that salesperson person number 16 had the most sales. We can also group by multiple columns. So let's say we want also the order date. Add another column here, and we also group by this column. Now when we run this, we have now the number of sales per combination of salesperson, person ID, and order date. So most of them only have one sale, but if we scroll through here, there are some dates and salespersons where they have multiple sales on one day. But as stated before, all columns that I want to select here that are not part of an aggregation need to be part of the group by. So what happens if I don't group by order date? I will get an error. And the error message is exactly stating what I just did. So we have the column order date, which is invalid in the select list because it's not contained in either aggregate function or in the group by. Count is an aggregate function, and there are multiple other aggregated functions that we can also use. Let me copy in here another example. In this case, we are combining now multiple functionalities. We first calculate our product of unit price and quantity, and then we take the overall sum over a, for now, not existing group. Then this means over all lines. So in the end, we will get now one value. So the total sales over all lines is this big number. And now we can go ahead. We could also break this down by order ID. And if we want the order ID over here, as before, we need to have it in the group by. And then maybe we order it by the order ID. And now we can see the total amount of sales per order ID. So all the order lines combined with the sum are the sales of that order in total. Next to the sum, we could also add, for example, the average sales. And we count this the average sales. So the sales and the average sales are a little bit different. Pause here maybe and think about why. The reason being is for this one, order ID 1, we have sales and average sales equal. So all order lines of that order are the same. In this case, we have, looks like 2 orders. For order ID 2, we seem to have one order that is comprised of 2 order lines. So in total, they have 405, and the average is 202.5. Another one that we can use is the string aggregation. This one takes a column as a first parameter, like for example the unit price, and then how we want to combine them. In this case with a comma and then a blank. And now we have added our price list column. Order ID 1 only sold one type of products for 230. Order ID 2 sold 2 different products. One cost 32, the other one 13, and so on. And then we also have the maximum and minimum aggregation function, which we can run here. And there we see, okay, for the order ID 2, the highest sold unit price, the max function is 32, and the min function is 13. As stated before, the null value is a special one. Let's look at this result. In here, I added an asterisk. As you remember, that means all columns. So in this case, when I combine it with a count, that means like count all the rows that we have. In another column, I'm just counting the picked by person ID. As you remember, in that column, we do have some null values. And then I can see that this second calculation, picked orders, is lower than the orders. In here, we have all rows regardless of null. And here we only have picked orders, the count where picked by person ID is not null. Again, a thing where you need to be aware of null values. When you have a query like this, you can see the sales per order ID, nothing new here. Now let's say we only wanted to see those orders which have sales over 1000 in total. So let's have a look here and keep especially an eye on order ID 20. I will copy it out here as a comment. Now let's say we are only interested in the orders which have sales under 1000. So you might want to go ahead and say where our calculation unit price times quantity is smaller or equal to 1000. Should do the trick, right? Let's have a look. If I run this looks very, very good until I'm down here. Order ID 20 has now over 1000. Why is that? Pause for a moment to think about it. The reason is we are filtering the individual rows of the order lines, but afterwards we take the sum of all the rows together. What we really would want to do is we want to have the sum of the unit price times quantity smaller than 1000. But when I try to run this, I get an error because I am now mixing row level filters with aggregates. That does not work because, as you remember, first we do the filtering and afterwards we do the grouping. And the sum is running on the result of the group. So this comes too early. We cannot do that at this point in time. And therefore we have another keyword. This is the having keyword. And with having, we can say exactly this. So you can imagine having to be the where condition for the aggregates. And when I run this looks the same, but order ID 20 is now gone. So having is the where equivalent for the group by what the where is for the normal row logic. Now let's have a look at how to join data. Join data means that we have two or more tables and we want to bring them together side by side in one query. To do that, we need to define the join criteria, which defines which rows match to the other one of the other table or the other tables. So why do we even do something complicated like joining our tables instead of having like one big table that has all the data? In general, tables are used in relational databases to avoid redundancies. And then we join those tables together to query them as a whole. We always need to define one or more columns on how to join those two tables. When performing a join, we don't immediately change the underlying data, we just bring them together in one query. Let's look at a simple example. Let's say we have this first table and this second table. They both have, as you see, a column seller ID. And now we might perform an inner join by the column seller ID. And then the result is the following. As you can see, we still have all four orders, but on the seller side, we have done data and LN analytics twice because their seller IDs are 1 and 2 respectively, which are in the order table. The ELISA engineer row is not here, as when inner join only returns the ones that are available on both sides of the join. So what we just saw is the inner join, the one where we only return the rows where the join condition is met on both sides of the join. Then there's also a left join, which takes all rows from the left side and from the right side only the ones that are matching. The opposite operation is a right join, which takes all rows from the right side, but only the ones matching from the left side. And then there's also a full join, which takes all rows from both sides, regardless if the join condition is met on the left or right side. Let's start by looking at two tables, the orders and the order lines. So we have always one order, and an order can have multiple order lines. Let's have a look at those two tables. So on the order level, we define, for example, when the order was placed. And on the order line level, we have per order ID. For example, let's look at this example here. Order ID 46 has 2 line items. So there were 2 articles bought. And now we might want to join them together. So to do so, let's write a query which will use the inner join. We will start with the orders table, and then after the from follows the inner join, sales order lines. And now we need to specify one or more columns that we would want to join on. So on. And while I could do the following, I could say sales.orderlines.order ID shall be equal to sales.orders.order ID. I could run this, but there's a shorter way. As you see, we repeat ourselves here quite a lot. And here you would typically use aliases. So let's say the first one we call O, and the second one we call OL. We can put it directly after here. Also, an alternative would be to put an S here between. In the end, it's just the same. So this name OL is then what we can reuse over here. Instead of sales.orderlines, we can replace it with OL. And let's take this O and put it in over here. And I can run it again. And here we have our first inner join. And what we see now is that we have quite a lot of columns. Because now we have first from the left side, which in this case is the top side, all the columns of the orders table, and then followed afterwards all the columns from the order lines table. Now, you might be asking yourself, first I was talking about left and right, and now they are top and bottom. You might also write it down like this, and then it gets clear which is the left and right side. So this one is the left side, this one is the right side. But for better readability, you would put them typically in the next line. All right, now we might also specify the columns that we're interested in. And let me say, for example, I want to have the order ID. Now we have a problem. I already get these red squiggly lines because now both tables have an order ID column. We have this column here, which is the one from the orders. When I scroll here over, we have also the order ID table from the other table. So now we need to specify which of the two we want. In the end, as we joined on equality, they have both the same, but still we need to decide. So let's say I want this from the O. Orders. Now I'm specifying from this table, I want the order ID column, and let's maybe add some more columns. Let's say we're interested in the salesperson ID, and from the other table, OL, the order lines, let's take the order line ID. Maybe we're also interested in the unit price times our quantity, and we call this one order line revenue. And then I can run this. And now we see that we have a table consisting of just 4 columns mixed from both tables, and they are joined on the order ID. And now we could even feed this result, this table that we now generated on the fly, consisting of those both tables, and use it to do a group by. Group by, for example, from our salesperson ID, and then we might add a sum over here. And then, as you remember, when we do a group by with an aggregate, all columns need to be either part of the group by or of the aggregation, but they're not allowed to stand here alone. So in this case, I would either have to group by them by the order ID and the order line ID, but in this case, I will just remove it. And now I can run this. And here we have now the order revenue per salesperson. Now let's look at an example where we might not want to use an inner join, but for example, a left join. I have here now 2 tables, and we have the stock items. So in our warehouse, the items that we collect our stock on or count our stock on. And then we have the colors table. So which color does an item have? If I run this, I can see, okay, our bubble wrap dispenser in black has the color black. Seems to make sense because it's already in the name. But turns out now we have 128 rows. Now we are only showing, as you can see, colors are always filled. But we are only showing products now that do have a color. Maybe we have some products that don't have a color. If we switch this to a left join, we will see that suddenly we have 227 rows. As, for example, the USB food flash drive sushi roll does not have a color. And as you remember, null is not a value, it's more like a state. So we cannot ask for equality between those color ID columns. And now you can see from the left side, so if I write it again like this, we have all the rows. And from the right side, we have the colors when they are available, and we keep them as null if not. But in our database, there might also be colors where we don't have a product for them. How could we query for that? We could use a right join in this case. So let's run this. Now we take all the rows from the right side and only the matching from the left side. And here we immediately see the result. So there's azure and beige where we don't have any items with that color, but we still keep the row. So, and it's then null on the left side. And then we scroll down here and now the other ones all have a color. And there are even more colors without an item attached to them. But in practice, we would rarely use a right join because when we put it under each other, we would typically start to read from top to bottom. But when there's a right join involved, we suddenly need to think, okay, now this is the base table of our join, and now we need to look upwards. And what we can do, and what typically you would do in practice, is to switch it to left join, and then just switch around the tables that we are joining. So now we get the same result, because now the colors are our left side of the join, and we will take everything from the left side. When I run this, it works perfectly fine, and the result is the same. So my recommendation is to never actually use a right join, but always switch the order of the joined tables and make it a left join if you have that use case. And as you might guess, if we want to have the results of both tables, we could make it a full join. Now, when I run this, we will have 256 rows, which is the most that we had until now. Now we have items that don't have a color. And if I scroll down here, we also have colors that don't have an item attached to them. So this is then the full data set that we could query on those joined with the color ID. Now, let me bring in another query again. And in here, we will have our stock items and we left join to the colors based on color ID. So it's the same. But now here's a where condition added, where color name is black. What do you think will be the result? Let's have a look. Now we have all the rows that have color name equals to black, but we lost all the rows from the left side. You see, we don't have all rows from the stock items anymore. Why is that? Well, the where condition is evaluated after we do the join. So let's have a look first. What is the result of the join? This is the result of the join. And in here we have some rows which have the color black, and some have, for example, null or other columns. And when we feed this result into the filter where color name equals to black, we will only keep the rows where the color is black. So what do we do if we want to keep all the stock items, but only have the color black joined to them? And otherwise, for example, we want to get rid of blue and steel green here, but we want to still keep this row. Well, we will add the color name filter not to the where condition, but to the joining process. We will say we will join on the color ID and on the color name equals to black. Let's have a look at the result now. Now we still have all rows from stock items, but we will only see the color if it is black. If I scroll down here, you see we only have null or black. And for example, the green one, where we know it's green because the name of the product contains green, but we get a null here, even though there is a green color for that item, but we filtered away with this color name equals to black. If nothing is left, it's always filled up with null. Next up, we have a self join. A self join is used to join a table with itself. It does not have its own syntax, but it's rather implemented the inner join or left join that we already know. To perform a self join, we must use aliases, as we will be referencing the same table name twice. So we need to be able to distinguish them, but it's anyway recommended to always use aliases. And a typical use case for self-joins is, for example, to query hierarchies, which is what we are going to do now. We can, for example, query a hierarchy of employees and their respective manager. To demonstrate the self-join, I have attached another demo database, the Contoso Retail Data Warehouse database. And in here we have a table dim employee. And in here we have an employee key and a parent employee. So one employee has always a manager. And this is exactly what we want to query now. Let me paste in here a complete query. And what we are doing here is we are querying the dim employee and call it E as employee alias. And then we do an inner join again on the same table, dim employee, and we call it M. This indicates this is our manager. And then we join on M.employee key. So from the manager, we take the employee key, and this one shall be equal to the employee's parent employee key. So in other terms, the key of the manager shall be the parent key of the employee. And let me run this. Now we have successfully performed a self join with the inner join functionality. And we can see, for example, that the employee 1, Kim Abercrombie, has the manager, Peter Uitenbogart. And Zagif Hadaya has the same manager, again, Peter Uitenbogart. Now we have returned 292 rows. And let me switch this out for a left join, run this thing again. And there we have 293 rows, one more. Why is that? Well, the top employee, probably the CEO or the head of the sales organization in that company, does not have a manager in this table. So when we do a left join, we keep him. So even though he does not have a manager, he's still there. So there must now be somebody who does not have a manager. Let me scroll through, and here we have him. In the end, it turns out Peter Uitenbogart is the sales group manager, which in this hierarchy seems to be the highest level of employees. So for now, we only query the employee and its manager. But what if we have multiple hierarchy levels? So we have employees that have a manager who themselves also have a manager. And that's also something we have in this data source. Let me paste in here another query. And now we do a self join. I will bring this a bit down so we can see it in whole. Now we have 4 levels in here. So we have employees on level 1, 2, 3, and 4. And every time we join them to the upper level, employee 2 is joined to the parent of E1 and so on. And then we show them in those 4 levels. Let's run this. Now we can see Kim Abercrombie is directly under Peter Uitenbogart and no more because, Peter Uitenbogart is the highest level. But we have, for example, Yoichiro Okada, whose manager is Kim Abercrombie, who in turn, her manager or his manager is Peter Uitenbogart. And then there's nobody above. And if we scroll down here, there's even a 4-level hierarchy in here. So we have Kim Akers, who is managed by Terry Adams, then who is managed by Kirk Nason, and finally Peter Uitenbogart. The next join type we want to look at is the anti-join. It's again a conceptual join made up of the join types that we already know. This one is returning us the records which are not present in the base side of the join. So if the left side has rows for the matching condition, they will not be part of the result. It does not have its own syntax. It's implemented using the left or right join with where is null of the second table, so the referenced table. With this type of join, we can, for example, answer the question of give me a list of customers that did not place an order in the last month. Let's start by looking at the result of 2 queries. In the first query, we are querying the orders and we want to have the number of customers. We're using count distinct. This is a combination that you encounter in practice very often. We want the number of unique customer IDs that placed an order in January of 2015. And then in the second query, we will get the number of customers we know in total from our customers table. Let's run this. So we see that we have 590 customers who placed an order in that month. And in total, we have 663 customers. So the question that we can answer with an anti-join now is, who are those 73 missing customers? So, and this is then a query with our anti-join pattern. We come from the base table, which is our customers. In here we have all the customers, and then we do a left join to the orders based on the customer ID, and the order date shall be in that January of 2015. And now the important part is this one, where order ID is null. Let's first run it without that where condition. Now we see all customers, regardless whether they placed an order or not, because we do a left join. We keep all the rows from the base table. And now we add the where order ID is null. So then we will filter out this list only for the ones that do not have placed an order in that month. Running this, we get the list of 73 rows. Those are our customers that we now might target with marketing. And now we already arrived at the last join type. In this case, it's the cross join. And the cross join is used to create the Cartesian product between 2 tables. So all rows are combined with all rows regardless of whether there are any matches on join conditions which don't exist. So this means that the number of rows is multiplied, and that can get very big very fast, so always use it with caution only. It is often used for reporting purposes. So when we perform a cross-join between those two example tables, and we will arrive at a table that contains 2 times 2 rows, which means 4 rows, and we have the combination of all rows with each other from left and right side. One example where a cross-join might be useful is to show the number of employees per position and department, including position, which have 0 employees. Now we can use the result of the cross-join, which is the combination of every position and department, join it to an employee table where we have employees which have a position and a department. Then we can make an inner join between the result of the cross-join and this table to get to a final table where we have per position and department the number of employees. And this table then also contains the combinations where we have 0 employees. Like here we have 0 developers in the HR department. In the warehouse scheme, we have colors and packaging types of products. Let's have a look at them. From warehouse.colors, and we have warehouse.package types. So we have some colors, azure, beige, black, and so on, and we have some packaging types, bag, block, bottle, and so on. And now we also have a table where we have the actual items that we have in stock in our warehouse stock items. And these stock items have a color and an unit and outer packaging ID. Now let's say we want to have a list finally of all colors with all outer packaging IDs. So this means we need to cross join, and then we want to count how many items we have for each combination. So let's first go ahead and make a cross join to the packaging types from the colors. And we don't need to specify on which columns we want to join, as a cross join always joins all rows with each other. So let's have a look at this simple cross join. We have first all colors with the first packaging type, and if I scroll down here, we continue, we have all colors with the next packaging type, and so on. Now we need to see how many stock items we have for each combination. That means we want to take this result and do a left join to our stock items. Let's call them I. Now we give them also aliases, C for the colors, P for the packaging type. Then we join I.color equals to C.color ID, and I. Let's say we are interested in the outer packaging, not in the unit packaging, equals to P.package type ID. Now we have a result where we have at the last columns our items over here. Now we need to count them. So instead of star, we want to have, for example, C.color name. So we want to know which color it is. We want from the packaging table, we want packaging type name. And then we want the sum of this also for the moment, say for the moment, sum of stock item ID. And we call this num of items. And then whenever we do an aggregation and we have other columns, we need to also add our group by. Group by C.color name and P.package type name. Running this. Now we see that we have our number of items here, but what I'm doing here now is to make the sum of an ID. And if it's a sum of an ID 10, we get a 10 for each item added here. So that's not what we want. So we need to add a conditional logic in here. Case when stock item ID is null. If it's not found, then we add a 0. Otherwise, let's give it a 1. And now we are summing always the 1. So we count all the rows if the stock item ID is not null. And we're in the else case. Now running this, we see the number of items that we have for each combination. Most of them we don't have, but in between we see that we have some items which are not 0. For example, we have 5 items with steel gray in the packaging type each. In the last chapter, we were looking at join and how we can join 2 tables via their columns. Now we will be looking at set operators. Now we take 2 tables, but instead of joining them horizontally, we will stack them, so to say, on top of each other. So we will union the tables, or we subtract rows that exist in one or another. The first option we have is the union. The union is used to stack 2 tables on top of each other. The second option we have is the intersect. We use it to get only the intersecting area between 2 tables. And the last one is except. So from our table A, we retrieve all the rows that are not part of table B. Let's have a look at how joins and set operators act differently a little bit visually. So let's say we have those two small level tables, and when we do a full join on a column A equals to C, we will get the result shown here. So you can see they are next to each other. When we use a union, which is a set operator, we do stack them on top of each other. So we have more rows at the resulting table. So now let's look at one example. Here's a query where we would stack on top of each other using the union, the first select and the second select. The first select retrieves us customer names, and the second one the full name of people. If I run this, we will receive a list of all those names in one table. We have received now 1513 rows. Now let me add, instead of a union all. This means we take now all rows and also duplicates. When I run this, our resulting table has 1747 rows. So if I would go ahead and scroll through this list, I would then see duplicates suddenly. So when you want to keep duplicates, you would use the union all function. And if you want to remove duplicates, you would use the union. A thing that is special about the set operators in comparison to the join operators is that we have to have the same number of rows and the same types of rows. So if I went ahead and add here another column of the sales table, let me see what we have in here. For example, credit limit. So in my first query, I have 2 columns and the second one only 1. So if I run this now, I get an error. What I could do is add a hard-coded column here if I have no equivalent in the second table. Maybe I just add the value null for all the rows that are found in this table. When I run this now, this works. But now you see we have a lot of nulls here. If I scroll through, then later here we have entries that are then coming from this part of the union operator. What I could not do is add here a column where we receive some kind of string value. Let me check what we have. For example, the hashed password. So now we have a number over here and a string over here. If I try this does also not work because we are trying to convert between those data types and we did not explicitly do that. How we will do that explicitly, data conversion, is something we will have a look at later. But if I try to run it like this, it will not work because we have different types in here. Now let's have a look at the intersect. Let me remove these extra columns over here and replace our union with an intersect. Now when I run this, I have a result set with just 261 rows. And those are the names. For example, this Abel Spirelia. This person is in this table and also in this table. So we only get now the duplicate rows. And as you might guess, if we want to switch from an intersect to an accept, we would just replace those keywords here and we can run this as is. And now we will only get the customers that are not part of the people table. So in this case, this would probably be only companies that we see here now. Looks like that's the case. In the last chapter, we saw that with the union, we cannot mix different data types. We would have to, as I said, convert them between one another. In this chapter, we will be looking at data types and how we can convert between them. We will be looking at the numeric, string, and date and time data types, which are typically used in an SQL database. Here's for you a table of the most commonly used numeric data types in SQL. And there are mainly 2 categories. We have integer values and floating point numbers. And as you see, we have different sizes of them for the data usage, and this leads to a number range that they support. And you might ask, why not always use, for example, big int? Why should I even hassle with having tiny ints when they only go up to 255? Well, the bigger numbers always take more bytes. And if we look at those big int and tiny int, it's 8 byte versus 1 byte. And as you know, a byte is not very big. But imagine you have a big table with, let's say, 100 million rows, then you can imagine that it adds up quickly if you use a tiny int or a big int. Next up, we have our string data types. And in the string data types, we differentiate mainly between fixed number of characters and variable number of characters. And let's say you have a field in your data where you know it's a code, which is always exactly 10 characters long. Then this would make sense to store it in a char field, because you would spare the 2 bytes at the beginning, which define how long is the data that I'm storing now. But you could also store it in a varchar field, which is then always having 10 characters, and you would waste slightly more bytes. But I'd say in 99% of the cases, you would want to go with a varchar type, where you lose those 2 bytes at the beginning to declare how long is the text that's following now. But if it's less long than the maximum size defined in the database, then you would save bytes. Another thing that we see in here is a difference between, for example, varchar and nvarchar. This n at the beginning indicates that in here I can store Unicode characters. So if I have some special characters that I want to store and want to keep, I would need to use the nvarchar column, but the downside is that it always takes then 2 bytes instead of 1 byte to store a character in the database. And then last but not least, we have some binary data sets in here. You might argue that they are not string types, and you would be correct, but I just added them here because I did not want to add another slide, because binary and text types behave quite similar. Just that in here you would store binary data instead of character data. And last but not least, we have date and time data types. In here we distinguish mainly between dates, times, and a combination of them, date-time data types. And they all have, as you see, different precisions and data usages. Now let's have a look at implicit converting. So first of all, let me bring in a simple query where we add 123 plus 123. If we run it, no big surprise, 246. Those are 2 numbers that we add. Now let's have a look at what happens when we add numbers and strings. So first query, if we run this part, we add 2 numbers and we have a number as a result. No big surprise here. What happens if we add 2 texts? Well, they get merged together and put together in one text. So this is again a text as a result. But now let's add a number to a text. So what now implicitly happened was a conversion of this string to a number, and then those 2 numbers were added together. The reason why we did the mathematical addition instead of putting those 2 as texts together is because the data type of a number has a higher precedence in the data types as a string. You can also Google this. This is a data type precedence. There's a big list, but you can also just always figure this out on your own very quickly if you are in doubt. Let's have a look at a few more examples. If we add an integer and a floating point number, what's the result? The result is a floating point number, because a floating point has a higher precedence than the integer. If we divide a 5 with a 2, we get a 2. If we divide a 5 with a 2.0, so here we have a floating point 1, where we learned just that the floating point has higher precedence, and then we suddenly have a 2.5. And the last one that we have is we divide the 5.0 with a 2. And again, as this one has higher precedence than this one, we put them in the floating point calculation area. I guess by now you have the feeling that this would work, but just to show, I don't need to always hardcode those values. I can also put in here the columns from the database. And here we have an integer value, and here we have a decimal value, which is a floating point 1. So the result is a floating point result. But then there are also things that cannot implicitly be converted. Let's say we have a date and we have a date time 2 that we want to add. Those 2 types are invalid. There's no implicit conversion happening. And if we wanted to add those 2 columns, we would have to explicitly convert them instead of having the database implicitly converting them for us. So then let's have a look how we can explicitly convert them. Let's take this example again. We have here the 5 divided by 2. In the integer world, we arrive at the 2. But now we can go ahead and add an explicit conversion here. We can say we want to convert to the decimal data type with the length of 2 and 1 floating point precision, the number 5. And then divide the result of this conversion by 2. So in here we will arrive at a 5.0 internally. And when I run this, we switch now to the floating point calculation, because this one is now a floating point, a decimal. Another way to write exactly the same is a little bit a question of style and something that you might come across. You can also use the cast. So the convert is a T-SQL specific keyword. And then you have cast, which is more standardized SQL. And when you use a cast, you would have first the value that you want to cast as something else. So here you have the 5 first and then as decimal. The result and what internally happens is exactly the same. So now let's have a look at the float data type. We have the option to say, okay, a 0.0 will be a floating point number with 25 precision. So rather big one, takes a lot of space already, but it's imprecise. And we can then calculate the 0.0 plus a 0.1, and then another bigger calculation where we have a 0.0 and we always add 0.1. And when I run this, you will see that, okay, the first one is a 0, the second one is a 0.1, but the third one is not a 0.8, it's a 0.8000001. That happens because the float is not a precise representation of a 0.1. It's internally binary code, zeros and ones, and they never get to the full precision. But the advantage is it saves space. So if you don't care about precision, which is nearly never the case, you should not use the float type. Now, let me replace this calculation with a decimal. And when I run this, we get at the final result a 0.8. So this is a real 0.8. And this is a precise data type. So most of the time you want to make sure you use a precise data type, unless you really don't care about minor errors. So now what happens if you convert something that is too big for the data type? As you saw on the table, the bit can only take 2 values, 0 or 1. And now we try to convert a 2 into this data type, and then it becomes a 1. That's for all the numbers that are not 0 or 1. If I put in here a 0, it will be a 0. That is because bit has a special logic which says everything that is not 0 is considered a 1, so it's a true value. So because we use the bit to distinguish between true and false, 0 and 1. If we would do the same for the tiny int, something else happens. So the tiny int is a value that goes from 0 to 255. And if we try to convert a 265 to a tiny int, we get an overflow error stating that the value 256 does not fit in a tiny int. So it would have to be an int that will work. One thing that we can do to avoid the errors that we get is to, instead of convert, we can say try convert. And then let's say we make this again the tiny int. And now we receive a null. So it means I tried it, but I could not. But then instead of crashing the whole query, maybe I run multiple things at the same time, I just get a null back. And depending on your use case, it might be something that you want. Otherwise, obviously, this hides a little bit the error that you were producing there. So it needs to be used with caution. If I do the same with 255, obviously it works and it returns the value as we want it. This whole topic of conversations works just the same way for the strings. Let's have a look at a few examples. If we convert a 1 to 3 to a char of the length of 2, the number of 2 in parentheses here indicates how many chars do we have available. It returns just the first 2 chars. 1 and 2, and the last one is then lost with this explicit conversation. Now you heard from me that we could use the varchar to have a variable number of characters, but the maximum length again is 2. What is the result? Well, it's again 1, 2 because we cannot fit more than 2 characters in this defined data type. Obviously, if we made more space in here, let's say they are both 10 characters long, and we try to put this in and run those 2 things, we get the 1 to 3. So what's the difference now between var and varchar? There's one special function that we can use. It's the data length. So give me the data length of whatever I'm putting in here, and the same over here. So how many bytes are then stored in reality in the database? If I run this, we can see, okay, the char, which is 10 characters long, which means 10 bytes, and it's 10 bytes, even though we just store 3 in here. And then we have the varchar, which returns us a 3. That is not the real true. There's also another 2 bytes for the length in here when we have a varchar, but somehow this function is not returning that. So in reality, this would be a 10 and this would be a 5. But as you can see, storing variable length data is much better in a varchar than in a char, because the char always reserves the maximum number of bytes that are defined in the data type. So now let's look at the difference between, for example, varchar and nvarchar, where we are dealing with special characters. In this type, I have an example here with this average sign, and let's run the select here. And then we have hell question mark, because this is implicitly an varchar type, and varchar does not have Unicode available. And then all those characters that are unknown in that character space will be shown as a question mark. You might have seen that before. So what needs to be done is to not have it as a varchar, but as a Unicode varchar. And then we can specify an n in front here and run this, and then we get this sign back. But now it takes more space. But yeah, just at the runtime, now that I'm just querying it. But you can imagine when we store it in the database, storing more information, it takes more space. Then now let's have a look at the date and time conversions. Let's start with a built-in functionality getDate, which returns us the date. Let's just run this. So this one just returns the date of recording right now of my time here. And I can then go ahead and convert this date that we have just returned here. And let's say I only want the date part of that function or only the time part of that function. And I call the columns date and time so we can easily see. When I have the date result, it's the 1st of November of 2025 and the time, which is then 2 p.m. And then there are also these combined data types where I have the date time. And then, yeah, there's nothing happening between those two because the getDate already returns a date time object. Another thing that I can do is like hard code my date time object with text. This is in 2002, 0101 at 8 p.m. It's 999 milliseconds. And when I run this, I get back a date time object. But one thing that you might note here is that we have a little bit of rounding going on because the date time is not precise enough for 0.99. And another thing that I can use then is the datetime2 type. Let me paste in another example here where we will take the same string but convert it to a datetime2 with a precision of 3. This length of 3 means I have a precision for 3 decimal point milliseconds places available. And when I run this, I see, okay, now with a more precise data type, I get the 0.999 at the end. So there's always with the date times, you'll have to watch out if you need to support those milliseconds. But what happens if you have examples that are less obvious? Let's say we have a Monday, 3 December 2010, which is definitely not in the format that we had before. It's a little more wild, right? If I run this, I get an error. I cannot convert this to a datetime2 object because the format is not recognized. What you can try then, there's another built-in function, which is the parse function, which tries to make sense of whatever we have here. And then the syntax is like the cast syntax. So we have first the thing that we want, and then we cast it as something. And when I run this, in this case, it worked, right? So if you have data that comes in a particular format and the standard conversion and casting does not work, you might try to use the parse. The parse can also be used for numbers, for example. So you can try to parse a value like this. So if I try it with the convert, it does not work, right? Because here's a comma in between. And I can then instead use a parse as decimal using German format. If I run this, it does not work because the German format has a point first and then a comma later. So as you see, this is a, for example, US format. If I try to cast it as EN-US, this will work and returns the SQL version where we don't have any separators between the thousands. Another function that we can use is the format function. We use the format function to format dates or numbers into a string representation. For example, we have here the default formatting for the date. And this returns then a string of the date in a specified format. There are lists online that you can look, which is the standard date formats. And there you can see the values that you could put in here to get other formats. There's also a third parameter available where you can set the localization. So for example, we can give out this value in US format, which stays the same. But if we say we want to have it as German format, suddenly the thing is coming out in German language and the format might slightly change depending on the format that you give here. One thing I use very often in practice is to have the date and then I want to specify exactly, I want first the year, then the months, and then the days. And then I can run this, and I get back a string that's just in this format. comes in handy very often. Now I would like to show you the most commonly used mathematical functions. The first one is a quite simple function. It's the abs or absolute function. So the absolute value of a 1 is a 1. If I give it a 0, the value is a 0. But if I give it a negative 1, so this is the absolute value of a negative, then we get a +1. So you always return the positive value. Next up, we have the sign function. So we have the sign of 1, the sign of 0, the sign of a -1, and the sign of a -1 in the decimal space. And as you can see, we always get back a 1 that is either positive or negative or with a decimal place. So what is the real functionality of this? If I give it a -10, for example, and I run this, I also get a -1. So this is always giving a 1, which is positive, 0 or negative, and it keeps the data type, integer or decimal number. Next up, we have the rounding function. So with the rounding, we are rounding our values to a specified number of decimal places. Let's run this and look at the results. If we have the 123.45 rounded to 1 decimal place, we get the 123.50. So it's rounded to the first decimal place. The second example is where we have a value that is lower than 5, and then we are always rounding down. So now we get 0.40 back. When we round to 2 decimal places, obviously we have also the precision of 2 decimal places, so the result is the same number. When we are giving it a negative value, like here, the -1, we are rounding to whole numbers. So you can imagine that the last digit before the decimal point is the 0. So now we are rounding to this position. And then the result is a 120. The function also has a third parameter, which if we don't give it a null, it makes a truncation. So in this case, if we give it a null, it returns the value that we would expect, like with a normal round function. But when we have a 1 in the third place, it's not doing a normal round anymore, but it truncates. So it truncates everything that follows after the specified digit. So after this digit, which is a 4, everything else is just simply truncated. It's in the 4-0 as a result. The next functions that we have are the floor and ceiling. So with rounding, we saw before, we are rounding the number. With floor, we are always rounding off. And with ceiling, we are always rounding up values. So when I run this, you see that those functions, floor and ceiling, they are rounding to whole integer values. And floor is always rounding down. So we remove everything after the decimal place. And ceiling is always rounding up. So whenever we have something here, we put it, the value finally up to the next integer, 124 in this case. And rounding, just as before, works as we know. And then we also have functions built in for squaring, taking the square root or the power. I will run this now. You might pause if you want to look at the results in detail, but in general, they are just doing exactly what the name is. They are doing the square root, or the power function. Next up, we have the random function, rand, and I will run this now 2 times. And we see 2 times we got a different value back, a random value. The rand function returns us a value between 0 or bigger or equal to 0 and smaller than 1. The random function also takes a seed. So if I give it a seed, for example, the 10, it will always return the same value. So it's randomly produced, but we can make sure that this random value is always returning the same. This makes sense if you're like testing some function and you want to make sure every run runs with the same value. But now let's have a look how this works when we give it a column. And then we want the second column, a rand column. And now when we run this, we see that we have the same random value for every row, because internally one query returns us one seed, and the seed is reused for every row. But this is most probably not what we want, right? Most of the time we would want one random value for every row. So now we need to get a little bit inventive and generate a seed that is changing for every row randomly. And for that, we can use a function called newID, which generates a new GUID for every row that we have here. So this is a global unique identifier. But we cannot directly funnel it into the random function as a seed, because if we try to run this, we have a problem. We have a unique identifier, and the random function only takes integer values as a seed. So we need to transform this new ID into a seed. And to do so, we have another function which generates us a hash value. So it's an integer based on the value in a string format, for example, that we give it. So this would be the checksum function. So if we run this new ID inside of a checksum, if I run this, we see that we get a seemingly random value back for every row. And now we can take this combination and give this into our random function. Now when we run this, we truly have random values for every row. Just as with a mathematical function to manipulate numeric data, we have string functions to manipulate text data. The first one we will be looking at is the len function for length. So how many characters do we have in here? The hello world has a length of 11. So we have 5 plus a space plus another 5. And as you can see, the empty space is also a character. If I run this, we have 12. But quite a peculiarity, the trailing spaces, if I add here 1, they don't count. So all the spaces are included except for the ones at the end. In contrast to the data length function that we saw earlier, where we count the bytes, here we only really count the characters. So if I make it a Unicode string, the length is still 12 because we have 12 characters in here. Next up, we have upper and lower. So upper function makes everything in capital letters and lower function everything in lower letters. Let's have a look at the result of this query. So we have the all caps hello world, all lower hello world. And if we have numbers as strings, they are unchanged by those two. Now let's look at left and right functions. The left function takes the number of characters from the left of a string, and the right function the number of characters from the right. Let's have a look at the result. And we get hell, the first 3 characters, or world, the last 4 characters when we do a write. Now let's look at an example where we do the select of the full name from application.people. And we want additionally the char index of the character, a space, a blank character, and also from the full name column. And we call this char index space. If I run this, we can see now at which character index we find the first occurrence of the space. So in this case, when we have alala, we have first 7 characters, and the 8th is the space in between first name and last name. And this is in the result that we get with the char index. And with this function, we can then go ahead and combine this with the other functions that we already know. So let's say we copy this one again and we make a new column. And let's say we do a left of the full name again. And then how many characters? Let's give here the result of the char index back. And then we call this first name. If I run this, now we have dynamically extracted the first name from this character over here. Obviously, this only works if we only have one first name in the full name column. If we had 2 first names, we would need another logic. The next function I would like to show you is the substring function. And this one takes the first parameter, the string or string column, and then we have an index, from which index, and then in how many characters. So this reads as from this string, I want from position 3, I want 5 characters. So let's have a look at the result. So I get the 1, 2, 3 from this character on. I get 1, 2, 3, 4, 5 characters as I specified in the third parameter. This is a substring function. The next set of functions I would like to show you are trim functions. So let's say we have a small little text here, blank, hello world, space, hello world, another space. We can use the ltrim function, which takes a string. And if I run this, we removed the space at the beginning. It's the left trim. Next, we have the right trim. Now we have the space at the beginning again, and it's not here at the end, but obviously we don't see it because it all looks like white space. But this is what right trim does. And then there's also the trim function, which trims at both the beginning and the end. When I use an L or R trim, I can also add a second parameter, which shall trim specified characters from the beginning or end. So in this case, I want to remove the H at the beginning. Now, when I run this, nothing happened because this string starts with a white space. But if I remove the white space here, it starts with an H now, which is also the one that I'm searching for. And then I'm trimming the H at the beginning. And I can also look for more than just one character. I can also say trim everything that begins with hell. And then we continue with a world. So you can see this trims all the occurrences of those characters. With trim, I can do the same, but the syntax looks slightly different. I would have to first specify what I want to trim, and then I add here a from, and then from which string I trim it. If I run this, the result is the same. Let me run this again with an H, and then we have the other result again. The next function I would like to show you is the replace function. The replace function searches in a given string for the first occurrence and replaces it with a second occurrence. So in this case, here's a hello world without a space in between, and I will search for hello and replace it with hello with a space at the end. Running this, we get hello space world. When I replace the third parameter with a null value, you see that the result is also null. So this is something to watch out for when using replace, and here we would not have hard-coded values, but then column references, which might contain null. The result will also be null. And with all these string functions, you can always combine them and use them in conjunction. And I would like to show you now one example where we will be extracting information from the website URL column. So first of all, let's have a look at it. This one here is a comment. So we have the website URL in the format http://www.tailspintoys.com with some sub-URLs. And if I scroll down here, there are also some wingtip toys or Microsoft website URLs. And now our goal is to extract the domain. So I want the result of tailspintoys.com. And now we can go ahead and we say, okay, we make now a combination. In here, first we replace from website URL the starting part, right? http://www. This is what I'm replacing with nothing. So here's nothing inside here. So let's first see what this part does. I would put it here and we will just have a look at this sub result. In the sub result, the replace result is then we have the part after the first dot here, right? tailspintoys.com, but we still have the ending here, which we might not want to have. So this is when we continue with our logic with the second part here. In here, we give the same result, but from this result, so this is what we are now looking at, we search for the char index of the dot. So the first dot in this string would be over here. So we count the characters until here, and then we add 3 because it's always .com. Obviously, this only works for this result. You might have shorter top-level domains like .de, but for the sake of this example, let's say they are all 3 characters long. And then the result of this calculation in total is exactly the length until here, until the first slash. And then we use this to make a left. From this result, we take the number of characters until here, and this is in our result. And when we run this, we see that we only have the domain here. And this is how you can then stack together those string functions. Is always a little bit finicky until you have the final logic. But what you need to be aware of is to know all the functions that you have available, and then you will be able to figure out how to stack them together to get the result that you want. All right, the next thing I would like to look at is how we can concat our strings. One thing that we know already is we can add the plus sign in between of them and they will be put together. But there's also a dedicated concat function, which does more or less the same. So I have the first parameter and I have a second parameter in here. It's in the world, and I can concat them like this. Running this, the result looks the same. This leaves the question, why do I have 2 options and which one should I use? Well, let's have a look at the following example. If I have hello plus world plus null, or I have the same but with a concat. Now we see the plus version. When there's one null in there, the result is a null. And with concat, we still get the non-null parts as our result, which is, I would argue, most of the time what we want. So recommendation would be always use concat to concatenate strings. Don't use the plus sign on strings. The last type of functions that we are going to look at now are date and time functions, and how we can use them to manipulate dates and times. Here we have a function to get the current date and time, this date time, and with date part we can extract respective intervals from our data. Running this, we get first time of recording, then we have the day, then the date part months, the year, the hour, minute, second, millisecond, and even nanoseconds we can extract here with the date part function. As you are often interested, for example, in the year of a date, there's also a shorthand, which is just a function year. And when you give the year this datetime or month or day, then we can exactly get the same functionality. So this is also the date part function, but a shorthand for those specific datetimes. But this does not work for all. Like if I would try it for the hour part and give it the sysDateTime, this will not work. Hour is not a built-in function. So if you want the hour, you really need to use the date part. Those three parts are available directly as individual functions. And then besides date part, we also have the date name function, and we can give the same parameters. And running this, we get the data in the current localization the database is running in, and we get all those values here. The dateAdd function gives us the option to add an interval and the number of intervals we want to add. So in this case, we have a function that adds 1 day to this date time and respectively another one month. Let's run this. And then we see from the 8th to the 9th or from the November to the December. And you can also give negative values here, -1 month, and then we are back to the October. And when working with this functionality, we have to watch out for the number of decimal places that we have in specific date types. For example, I have a datetime object here, which is the 1st of January in 2022 at 0 o'clock with nothing else there. When I run this and I add 1 millisecond, you see that nothing changed, even though this should be the millisecond level. Why is that? Well, let's try to add 2 milliseconds, and then suddenly we are at 0.003 instead of 2. Well, the reason is the data type has a precision of 3 millisecond steps, so you cannot go on the individual millisecond level. If you need that, you can, for example, use the datetime2 data type with a precision of 3 decimal points. When I run this, we see here at the end the 2. And technically, we did not waste more bytes now. Datetime is more like a legacy data type, and you should really always use datetime2. And another benefit of datetime2 is, if you need it, you would obviously rarely do so, but you can go up to 7 decimal points of precision here. And when I run this, you get more zeros. And with this precision, we could even go ahead and add 100 nanoseconds, which would then be the last precision that we can add here. The next function is the dateDiff function. This one comes always handy if you want to see how many, for example, days are between two dates. Running this, the days between 2000 and the current date would be 9,000 and something days. One thing to watch out for is, let's say we want to count the milliseconds, and when we run this, we get an overflow error, which means there's too much data for the returned data type, which is an int. If you remember, int goes up to something like 3 billion, but there are more milliseconds here. And what we can do is then use dateDiff big. Running this, we get the result here of many milliseconds since 2000. Now a small little riddle for you. Do you think those two columns will be the same value if I run it now? Pause and think about it if you want to. If I run it, there are 2 and 3 days respectively, because the dateDiff function is leap year aware. One of them has more days at the end of February. For now, we have always given our date as a parameter, but there's also a date from parts function which lets us generate dates. So in this case, we have 3 parameters: first the year, then the month, and then the day. If I run this, we get back a date value with the specified parameters. The same can be done with the time. Let's go ahead and say time from parts. And in this case, we have more parameters. First, we have the hour, then the minute, then the seconds, fractions of a second. Let's say we put in here a big one, and the precision. You remember the number of decimal places for the milliseconds or even nanosecond level. And when I run this, I get back a time value with those specified parameters. And as you might guess, there's also the date time from parts and also date time 2 from parts. In this case, first I give the parameters for the date, then I give the parameters for the time, and this all together returns us a datetime 2 object with the date and the time. All right, let's continue with another example. We can have a look at the invoice date from wide word importers dot sales dot invoices. And in here we see some dates. Now let's say we want to know always the end of months of each value. Now we can use the EO months to get the end of months of each individual value. So I take the end of months and as a parameter, I gave it our invoice date and we run it. Then we always have here the last date of the respective months. If I scroll down here a little bit, we see, okay, this also works then for other months as well. Now you might think, okay, when we have an end of months function, we would also probably have a first of month, and I give it the same parameter. But unfortunately, this does not work because this is not a built-in function. But we saw before, we have the date from parts, so it's not really a big issue. We can just say, give me the year of the invoice date and the months of the invoice date. And then if we always want the first of the months, it's always the first. Running this, we always get then the first of the months. So this would be the equivalent to the end of months function if we want to have the same functionality built with the built-in tools. If you're working with data that is spanning multiple time zones and you want to somehow get a common denominator, you need to think about how to handle those time zones. And the most reasonable thing to do would be to work with UTC time, so the coordinated universal time. Let me run the following query to see some examples. If we run the normal sysDateTime function, we get back the 12:39 of 8 of November, where I am currently located right now in Europe. And then there's a function to get the UTC date time, which is then 1 hour earlier. Then we have the getUTCDate function, which does more or less the same with less precision. And a very interesting function is the sysDateTime offset. So with this one, I get my current date, but I get the information that I am in a time zone currently where the date is +1. So if I wanted to convert this back to UTC, I could then go ahead and take the 12 minus the 1 hour, and then I'm at the 11, which would be UTC. And when I'm working with these offsets, I can also retrieve the values at specified time zones. For example, Western Europe Standard Time or US Eastern Standard Time. Let's look at the results. The first one retrieves what we currently saw, because I am currently in the Western Europe Standard Time zone. But in US Eastern, it would be 6 a.m. with 5 hours behind UTC. So how can you find out which values you can give in here? Here's one query that you can run to get all the time zones available in your current SQL server. And then you can go ahead through here and get this string specified time zone. And this then wraps up date and time functions. Imagine you have a big query with 10 joins, and when you look at it after 2 months, you don't really understand what's going on there. This is where subqueries come in handy. With subqueries, you can define, as the name suggests, small little subqueries that you can later then combine together to a bigger query. And the benefit is definitely you can really see what those individual parts are doing and then reason what the bigger query is doing in total without having to look at it as a whole. So it's definitely a good thing to manage your bigger queries into smaller manageable chunks. Let's start with a simple query that we have here. We have a query based on the order lines table. And the first location where I can add a subquery is as a new column in our select. I do that by putting it around with parentheses. And now I can select anything. I can, for example, in here select 1. A very simple query that I could individually execute. It just returns a 1. If I run this in the context as a subquery of this outer query here, it returns me a 1 in every row. But instead of adding a 1 to all rows, which is rather unspectacular, we can, for example, put in here the following subquery. Select the average of quantity times unit price from the same table. We have to give them here a different alias in this case, which is in the O2. And I could run this individually, and this will return just one value. But now I can put this one value inside this bigger query. And now I see another information here. Now I could, for example, calculate, is the order line revenue of the one that I'm looking at right now, is it bigger or smaller than the average order line revenue? That would be one use case for this. We call this one an uncorrelated subquery because there's no correlation to the outer query. But then there are also correlated queries. Let me take the same part, and now we will add a correlation. We do this using the where clause. And first of all, I need to give it a new name. Let's call this one our O3. And then I can say where O3 dot order ID equals to O1 dot order ID. O1, our outer query in this case. So I'm establishing now a connection between the inner query, the O3, and the outer query, the O1. And now let's run this one. And now what we have is a rather interesting result. The first line in here is only one order line for order ID 1. So the order line revenue of that one line is 2,300, and the average order line revenue is also 2,300. But the order ID 2 is an example where we have two order lines on the same order. So we have two order line values, but then we have over here an average order line revenue, which is the same. So what we have here now is rather interesting. The order ID 2 is now the ID that we are correlating our queries on. And in the last column, the average order line revenue, we have 2 times the value of 202.5, which is the average of those two values, the ones that belong to the order ID 2. So as you see, the correlated subquery is a very powerful tool that is good for you to have in your SQL belt. Now let's have a look at the second location where we can use our subqueries. We have here a very simple query, and I will use this now as a subquery in our from area. So I can say select everything from, and then I can put in here the result of our subquery. And in this case, I need to give it an alias, otherwise it will not work. Now I run this, the result is the same, but I have now selected from our subquery. Obviously, this does not yet make much sense, but I can treat this now as a normal table that I'm selecting from. And I could go ahead and say, okay, I want to inner join this now to the orders. Order ID equals to OL dot order ID. And running this, I have another query. Still, does not seem very useful, but you can imagine that now we are looking at a 3-line join. If we are going ahead and come up with a thing that goes over, for example, 20 lines, then it definitely is a benefit that we have the chance to go in here individually and look what happens. For example, the subquery might already do some kind of logic. So where the order ID is bigger or equal to 100. So whatever you want to do in here, that works then with the bigger outer query, and you have localized your logic in here. Still, you could put this where clause in the outer query here, but believe me, if these queries grow in size, you are very happy to have extracted individual logics that you can individually look at the result and test them. Now let's look at in and exists. You probably remember the in keyword that we can use, for example, in where clauses, where in, and then a list of values which are hard-coded in here. This is rather undynamic, and depending on the data, when it changes, we might have to always adjust our IDs here. This is an area where we very often use subqueries. So instead of hard-coding values that I'm interested in, I can query them, for example, like this. So this query returns the distinct order IDs from the orders table where the order date is equal to the 1st of January of 2013. And this whole result can then be executed in conjunction with the outer query here. And then we have only the lines where the order date is equal to 2013. Very powerful, both of these functionalities together. Now let's have a look at the exists keyword. So this is also something that we can query. And we can then have here a correlation. So let's have a look what we have here. We have an outer query, and then we have a where exists. And this exists is then followed by an inner query. And this inner query returns something, whatever it is. We don't need to specify anything here. Typically you put in here 1, does not really matter. What matters is that we select something from the orders table where the order date is in 2013, 1st of January. And here we have a correlation now. The inner one is the O. So the order ID O table is equal to the OL, the order lines table that comes from outside. So here again, we have a correlation between those two tables. And we will now only return rows from the order line tables if there is an order on the 1st of January 2013. So the result of this query is the same as we had before with the in keyword. So you might wonder, why should I even bother with the exists, which looks a little more complicated? Well, the difference is that we can now check for the existence where 2 or more columns are equal to each other from the outer and the inner. This is something we cannot do with the in. So syntax-wise, it would look like this. Now we will only return rows when the order ID is equal and also the picking completed when is equal. In this database, they are equal, but when working with the in keyword, you will sometimes get to the situation where you would want to have those 2 conditions met. And then it's good to know that there is a version exists where you can add 2 or more columns that you want to have checked for equality. Another thing that you can do is add a not. Not exists or before not in. This would also be possible. And then you get the negation. And when you run the exists or in combination with a not, then there is a subtle difference between those two. Let's have a look. I have 2 queries which look like they should be doing more or less the same. First one is orders picked by person not in, and then here's a subquery for the distinct list of picked by person IDs, or again from the sales. In this case, not exists, and then select something from orders, and here's the correlation picked by person ID equals to picked by person ID. When I run those 2 queries, we see the first one does not return anything, and the second one does return the data that we most probably want in this case. Why is it? Let's have a look at the result of this inner query here. And we see that we return null or some picked by person IDs. Let's have a look at the result of the 2 queries again. In the orders table, when we look at the picked by person ID, they are null in this database. And there's a subtle difference. If we do not in, and there is a null in here, it will not return that row. In here, we did return a null row. And this is a subtle difference how those 2 versions, not in or not exist, treat the null value. Not in will not return any null values if they are in here. But the exists version will also return the rows where we have a not exists going on a null column. That's just something to keep in mind. When you use them with not in conjunction, you need to watch out for null values. When you use subqueries to divide the logics within your query, it can still get a little bit messy if you have, let's say, many subqueries within one query or subqueries based on other subqueries, which is also possible. And to somehow structure this more clear, you can use common table expressions. If, for example, you have a query like this, where you have an inner query and an outer query, the inner query is giving you the order revenue for every order, and then the outer one is generating an average order revenue. This works perfectly fine. If we run it, we get back one value. But we could also rewrite this using a common table expression. And in this case, we would take our subquery content here and put it before the query itself. And it starts with the keyword with, and then we need to give it a name. In this case, we might want to name it order revenue as, and then in parentheses, we put the query. And then we can reference this name later in the query. So instead of this subquery from, we say from our order revenue. We don't need this anymore. So now we can run this and it works perfectly fine. So now you have it more clear, separated that this part is one query, which is then reused with this name later on in the query. When you have bigger queries, this comes in very handy to also visually separate the individual parts of a query. If you have multiple subqueries, you would then separate them with a comma in between of them. So let's say we have another subquery here, and let's name this one the average order revenue. And I will just put in what we had before. So This does not make much sense, but just so you see that it's possible, in the second one, I can reference the first one, and then later from the final one, I can say select everything from this new name. This works perfectly fine. So you can imagine you can add different things in here, and as you have seen, you can even reference the previous ones within this chain of subqueries. So these are the common table expressions. Another thing you can do with common table expressions are recursive queries. They are looking a little bit complicated, and they also are, but let's have a look at this example. In here, we start out with selecting one date. This in our case is the start date where our recursion starts. And then we have a union all from the same name. You see, the common table expression is called dates, and it's also referencing dates itself. And for every iteration, it will add, in this case, one day to the column date, which we did here before, until the end of that year in this case. And if I try to run this, I will get an error stating that I have reached the maximum number of 100 iterations. So it was 100 times calling itself, because as you see, there are 365 days in between here. So this is like a protection, so we don't overwhelm the server with endlessly running queries. But if we are sure what we are doing and we really want this, which I'd say in this case we want, we can say we add the option max recursion 0. So this means I add an option to this query. The option is called max recursion, so how many recursions are maximum allowed. And if we add a 0, it means indefinitely. So if I try to run it now, we have generated now a table, query result with 366 rows. So in the end, we also have the first one from the last date. So we might probably want to do smaller instead of smaller than equal. Now we are having a full year. So this can come in handy if, for example, you want to do in reporting based on a specific date where the dates might not be present in the dataset. You remember the anti-join use case. This is something you very often will find in practice that is used in conjunction. I know the syntax is a little bit confusing if you saw it now for the first time, but I think it's good that you have seen that it's possible, and when you need it, reference back to this video or just quickly Google it how to write it, and then you will get your hang on it. When you want to export data, it highly depends on your client tool. So in this case, I'm using the SQL Server Management Studio. And in here, I have, for example, an option to say copy with headers as a pop-up menu here. And then I can go ahead and put it, copy, paste into an Excel file. So this is like the easiest version if you just want data out there to share it with your coworkers. Another option would be to use the BCP tool, which also gets installed together with your SSMS. So you can hit CMD and give in here a command we call the BCP tool, and from white world importers.sales.orders, this one, we can say out, give it a folder and a connection. Running this, we have our data exported over here. When working with data, you might come across the term CRUD. CRUD stands for create, read, update, and delete. So everything that you might do with data. And for now, we were only selecting data. So we were only looking at the read part of the CRUD term. In this chapter, we will be looking at how we can create, which is insert in SQL terms, or update or delete our data. And then we will also have a look at the merge statement, which combines those updates and deletes and inserts in specific cases. First of all, let's have a look at how we can insert data. And to do that, we will be first creating a new table. As you can see here in the tables of the White World Importers database, they are always within a specific schema. And to not overwrite existing things, we will go ahead and create our own schema and call it def. If I run this, it completes successfully. So how do we get data in there now? I have here a simple query which takes just the first 10 rows from the order lines table, and we have a keyword into def. This is the schema that we just created, and then we give it a table name. Running this, we created a table with 10 rows. Now let me refresh over here, and there we have it. Now we have a def order lines table, and we can already query it now. When I run this, we see our 10 rows that we have just previously inserted. Once a table exists, we can use the insert into statement. For example, insert into def.orderlines in those 3 columns, and then we can hard code values, for example, in here. I can run this. 1 row is affected. Let's have a look. 1, 2, and 3.00, the values that we just added there. So now this table has 3 columns. And what happens if I try to add 2 values without specifying the columns that they should go into? If I run this, I will get an error. The number of values does not match the number of columns. So we could do, for example, add a null here. If we just don't know one of the values and still want to add it. If I run this works perfectly fine. And there we have now our new entry with null as the last one. While this works, this is something I would not recommend. You should always specify the columns that you want to insert into, because if somebody else changes the order of rows, how they are ordered in our table, they suddenly get inserted somewhere else if you have a query that you want to run on a regular basis. So best practice, always specify the column names where you want to insert and then use the same order down here. Once a table exists, I can also use the insert into syntax, but using a select query result. So if I run this works perfectly fine. And there you have the rest of the results. After inserting our data now, let's have a look how we can update our data. Let's have a look at this example. We have the order line ID is twice in our table. If we want to update it now, we would say instead of select from, we say update and then the table name without a from, but instead we will say set, for example, unit price equal to 4.00, where order line ID is 1. Running this, that worked perfectly fine. And now let's select the data again. And now we see we have successfully updated it to 4. We can also update multiple columns at the same time when we comma separate them. So let's say we have unit price will be 5 this time and quantity 10. Let's update it and see what we got. Perfect. Now let's have a look at how we can delete line ID 1. And then we have, instead of an update, we go ahead and say delete from def order lines. And we can also add a where condition here. If we run this, and then let's have a look at the entries in the table, and there's no more row with a 1. Now let's have a look at the merge statement. The merge statement is used to merge differences from one table into another. It can perform insert, update, and delete operations in one go, depending on the differences found. You would typically use it to synchronize 2 tables, maybe in ETL jobs if you are thinking about a data warehouse. It is joining those tables, and by joining them, it identifies new rows, changed rows, or obsolete rows. So we have a left side of a join, a source table, and then a target table. Everything that is blue is new. Everything that's black there in the middle is changed, and obsolete rows are only in the target table. The first case is not matched by the target table, which means we perform an insert. In the middle, we have rows that need updating. And on the right side, we have rows missing in the source table that are in the target table. So in the target table, they shall be deleted. Let's have a look then how we implement this. First of all, we need some tables to work with. So let's create a from table and a to table. And then let's have a look at those 2. So in the from table, we have the ID 1, where the name is data new name. And the same ID in the to table has the name data. So there's a name change for ID 1. ID 2 is available in the target table, but missing in the source. And then we have a new record here. The ID 3 will be an insert in the target table. Now let's add the merge statement. So it starts with the keyword merge, and then what table we want to merge into. This is our target. And then we are using our from table as our source. So we want to merge from table into to table. And we join them, as you saw before, we need to join them on ID of source equals target. So we join them on this column. If we identified insert, which means we have a not matched found in the target, then we will insert this row in the target from the source. For updates, we will have a match. So we found rows in both tables. In this case, this will be the row 1, where we have the 1 ID in both tables. Then we will perform an update on the target with the value of the source. The data new name will be put in here via an update. And then the last case is the delete. So when there's no match in the source, then we perform a delete. That would be ln analytics, because we don't have a 2 anymore in the source. And then we can also add an output here, which just gives us some useful diagnostics about what happened and what actions performed. And when I run all this, I get the output, right? We had an insert for ELISA engineer ID3. We had an update from data to data new name, and we had a delete. ln analytics is gone. So now let's have a look at the two tables. They are now exactly the same. This is exactly the use case for the merge statement. We make sure that we synchronize from one table into another. We have created now our first table by simply selecting data from one table and inserting it into another one. But this is not really a structured process, right? We don't really know for now what we are actually doing there. And unfortunately, we need to cover a little bit of theory now, a little bit of relational database design principles, so we can reap the benefits like data integrity, atomicity of transactions, and make sure that our security can be set up correctly. And therefore, we will be looking at normalization. This is what this is called. And I will also show you what primary and foreign keys are and why we need them. So that after this chapter, we have our theory set and we can actually go ahead and create our tables in the SQL server. Let's say you have the following employee data and you want to store it now in your database. While you could put it just as is into a new table, this is not how you should do it. And you would want to go through a process called normalization to end up with a set of tables where you can have defined relations between the types of data that you are about to store. And this is exactly what we are going to do now. To bring our data into the first normal form, there are 3 rules that we need to follow. The first rule is that there shall only be single value attributes, atomicity. So our employee name can be split into the columns first name and last name. The department stays as is. And then the skills column is like a combination of different things, right? You have the skill, and behind it in parentheses, you have the skill level of the respective skill, and then followed by multiple more skills potentially. So we could end up with having 2 times a set of skills and skills level columns. Then the zip stays as is, the city stays as is, and the salary stays as is. The next rule is that each attribute has a unique name. So we have now 2 times the skills column and 2 times the skills level column. This is something we cannot have. So we would rather put those 2 into rows. As you can see here, the first row for data is now split into 2 rows, and one has a skill SQL. The second one has a skill data visualization with their respective skills level. The third rule is that the order in which the data is stored doesn't matter. So if you would have like an order that is needed to have your data stored in a meaningful manner, this is not allowed in the first normal form. In our case, this is not the case. We have nothing to do to fulfill this rule. To fulfill the second normal form, we have to fulfill all the rules of the first normal form, plus there shall be no partial dependency, which means that all non-key attributes are fully dependent on a primary key. A primary key is something we use to identify one row exactly within a table. In our case, after we split the skills into multiple rows, we don't even have something to identify our employee, right? We have, for example, data in here 2 times, 2 rows. This is something we cannot have if we want to have the second normal form. So first of all, we need an employee ID. For example, we give it a numeric value, like the number 1 would be identifying data. But then we will have to leave all the information that is not directly attached to our employee ID in a separate table. So in this case, we will extract, for example, a skill table where we have a skill ID and a skill. So in here we have one skill only once. And you see, for example, SQL is now only in 1 row. Before it was in 3 rows. And then we also need a so-called bridge table, our employee skill in this case. In here we will have a column for the employee ID and a skill ID. So this is like a matching table where we can say as you look at the first row, employee ID 1, which is .data, with the skill ID 1, which is SQL, has the level expert. With this setup, we have stored the same data. So now you might ask, but why should I do that? Imagine the skill SQL is renamed to new SQL in the future. In our new setup, you would only have to edit one cell in here, rename SQL to new SQL. In our old setup, you would have to make sure that all appearances of SQL are renamed. But what if somehow the rename process fails after having renamed half of the columns? You would end up in a situation where you have the skill SQL, sometimes called SQL, and in other times called new SQL. So this goes against our desire for data integrity. You want to have only one name for one thing. Let's have a closer look what a primary key is actually. So it's used to identify records within the table. So in our example, it was the employee ID. There's only one primary key allowed per table. So there's only one key that is identifying a row within our key. It's also possible to have the primary key as a combination of multiple columns if there are some candidates in your data where you know this combination of values uniquely identifies my rows. Primary keys cannot be null, and they shall ideally never change. So once it's set, it should forever be able to identify one record. In our example, we chose an employee ID which is just numbers 1, 2, 3. They inherit no real meaning for the employee, and so we can make sure they never change. So the employee ID 1 will always be .data. And if, for example, .data leaves the company, we will make sure to never again use the employee ID 1 for another employee. So we will, in the history, always know employee ID 1 was .data in the past, and then nothing else happens with this ID. And then there are also foreign keys. They are used to establish robust relationships between parent and child tables. And it must reference either a primary key or a unique constraint. So in the case of a primary key, you make sure that whatever we point to in the related table, it is an identifier for that row. And the same holds true for the unique constraint. The unique constraint is a special constraint in the table that we can define, which makes sure that in a set of columns, there are only unique values in a row. In contrast to primary keys, foreign keys can be null. So you could imagine that we don't know where our future employee will live, so the zip might be null. The referenced keys must have comparable data types. So for example, if you have a reference to a number column, it shall also be a number column in the parent table. And we can also specify them over multiple columns. In our example, we had our position table where the position ID is our primary key. And then we had our employees, and in here we have the primary key is the employee ID, and the position ID is a foreign key, and this one is referencing the primary key of the position table. Now let's continue with the third normal form. The third normal form requires to be in the second normal form already, plus there shall be no transitive partial dependency, which means that all non-key attributes are fully dependent on a primary key. So where could we potentially violate this rule in our current setup? Well, let's look at our columns zip and city. In here you have the zip code 10,001 and the city New York. Now, if you change the zip to 90,001, you have to implicitly also change the city to Los Angeles. So the city is dependent on the zip, not on the employee ID. And therefore, we shall also exclude a dedicated zip table in which we have all the zip codes, and then we have the cities. And in our employee table, we will only have the zip code at the end. So if an employee relocates, you just have to switch the zip code in here and nothing else. There's no transitive partial dependency. And one last thing that we might want to do is, if we look at the salary table, we have the 120,000, a little over 110,000 and 10,000. If you think that this is a column that you might want to mathematically calculate on later, and you would want to have it as a number column, then the second one, a little over, is something we cannot really deal with. Well, we might replace a little over 110,000 with a null value. So you can make it a number column and, for example, calculate averages per department. But this is then up to you, the designer. How strict do you want to be? What are you going to do with the data? Does a little over 110,000 really mean something to you? Do you want to keep it? Or would having it as a number column be more valuable than keeping this value and maybe later correct the data in the database once you actually know how much the salary is? And the third normal form is typically what you stop at when you do normalizations. Just for you to know, in theory, there are even more normal forms that you might want to follow. You can read them up on these links, but typically in practice, the third normal form is what you are going for. And in the process of designing your tables, you would typically not use Excel as I did in this example. You would want to have a tool where you can define your relations and see it graphically. And those are entity relationship diagrams. And let's have a look at an example. And this is our small little database design in an ER diagram. So in the middle, we have our employee. Our employee has a primary key, employee ID, and has two foreign keys, one to the department and one to the zip. And then you can see there's a connection here to the department, which is a primary key in the department table, the department ID, and the same for the zip over here. And then up here, we have a bridge table, the employee skill, which connects our skills and levels to always one employee. So the primary key in this one is a combination of employee ID and skill ID, and it has a foreign key to the employee ID. It has a foreign key to the skill ID and a foreign key to the level ID. So as you see, a small little Excel table, if we want to put it in a third normal form into our database, it gets quite complicated. But the benefit that you reap is that you will store less data because you have less redundancy, and you will make sure that you never have data integrity violations. Now that we have our entity relationship diagram finished, it's time to actually go ahead and implement it. The first table we want to create would be our employee table. So I will go ahead and say create table. In the def schema, put in the table employee, and then in parentheses, I specify the columns that I want to give this table. Let me paste it here. So we have integer columns and varchar columns, and the names are over here. The zip column is a special one where we give it a default value. You'll see in a moment how this works. And another thing that we see here is a not null constraint. So this means whenever I want to enter a record in the employee table, the column first name must be not null. Otherwise, the database will reject those inserts. This is what you can use the not null constraint for. And now we create the table. Now let's enter a record into our newly created table. So we will be specifying, as we know already, the columns, and here we can add the default information for the third column, which is a zip. Let me run this. One record was affected, and now let's have a look how it looks in the database. All right, we have the record entered and the default value was set. So it's specified on the database table level, which is our default value. And now let's remove that one again. Next up, let's add all the other tables that we need for our ER diagram. So we have the employee skill table, the skill table, the level table, department table, and the zip table. And in here you see we expect very few individual skills, so a small int is most probably sufficient here. The same for the level. As before, let me run these statements, and we have our tables created. Once a table is created, we can not create it again with the same name because it will be running into an error, but there is the alter table keyword that we can use to alter existing tables. So in this case, let's alter our employee table and add a date of birth column. Running this works perfectly. One thing to be aware of when adding new columns with the not null constraint is this will only work if there are no records yet in the table. Otherwise, we would have a not null column and those values would be null, which is not permitted. So you may specify the null here or leave it out completely, then add the column, afterwards fill it, and then change the column again and make it not null. So how do we change a column after it already exists? There would be not the add column, but the alter column. And just to have something different now, let's do it a varchar, just so we know this works. Running this works perfectly. Let's have a look at the table, how it is now set up. And there we see the date of birth is a varchar. And then dropping it again is just as easy. We alter this table, but in this case, we drop the column. The date of birth is dropped again because it was not part of our original ER diagram. The last thing to cover in this creating and working with tables domain would be to drop tables. So first of all, let's create a dummy table, and then we can drop it using drop table and then dev.dummy, just the name, and that's already enough. Running this works perfectly. This is how we drop columns after they have already been created. For now, we have just created a bunch of tables, and except for the not null constraints for the first name and the last name, you can pretty much put whatever you want into those tables. Now, we want to make sure that the data integrity is provided by the database itself. And this is where constraints come into play. So we have the not null constraints that we already know. Primary and foreign key are things we conceptually know, but we never implemented it. And then there are also these unique constraints. And in general, we will be looking at those constraints in this chapter now. So first of all, let's have a look at our null constraints in action. If you remember, we created the last name column with a not null constraint, and now I try to add a value in here with null value. If I run this, I get an error. Cannot insert the value null into the column last name. The column does not allow nulls. This is what we use the constraints for, right? You protect our database against data where we know we will not want to accept it. Then let's go ahead and add values which will be accepted in our database. Works perfectly fine. Here we added a null, but this one is for the salary column, and the salary column does not have the not null constraint, so null is perfectly fine in this column. Let's have a look at the values we do have in there. All right, we have a null value now in the salary column. So what happens if we try to add a not null constraint to the salary column? You remember alter table dev.employee, alter column, salary, still the same type, but now with a not null. If I run this, I get an error because there is already a null value in that column, and so I cannot make it not null. I would have first to delete the row or update the row to a different value, and then I could add the null constraint. Now, you remember we wanted to have a primary key on the employee ID of the employee table. And to do that, we can say alter table dev.employee, add constraint of the type primary key on the column employee ID, and we call it PK. It's like a convention for primary key from employee table on that column. But you may name it or whatever you feel like. But now if I try to run it, I get an error because the employee ID column is nullable. And this is, if you remember, not allowed for primary keys. So what we would have to do first is to make our employee ID column not nullable. First I run this now, and then I can run this, and we have our primary key. Let's look in the tree view here how this table now looks like. Let me hit refresh and have our columns, and here we see now a small little key, which indicates this is our primary key, PK column for this table. Now let's do just the same for our department table. Another way to do it is to specify directly on creation. So for the skill table, let's first drop it all together and then recreate it, including the constraint. As you can see, constraint, then the name, PK, table name, column, primary key, and then define which column it is on. This also works like this perfectly fine. I will go ahead now and do the same for the other tables, but it's just a copy paste of the same logic, so I will not show it to you. All right, we have now set up all our primary keys, and now I could run, for example, the following query. Add a new employee with a new employee ID 9999, and I can run this. Nothing is stopping us from doing that. But do we always want to specify this value? I think not. We chose to give it a surrogate, which means our primary key is like an artificial number that has no business meaning. It has no meaning from the data itself. It would be a different case if maybe company-wide the employee ID is always the same, and you know, okay, employee A has employee ID B. But in our case, it's just an arbitrary number. And then it makes sense to define this column as an identity column. Let's have a look at what we have now. 1, 2, 3, and then suddenly a 99999. This is what we want to get rid of now. So first of all, let's delete this entry again. So maybe let's completely recreate our table. First of all, we drop it again, and then we recreate it. This time though, we specify our employee ID column as an identity column. And this one takes 2 parameters. The first one is where does it start? So the first value entered will be a 1. And then by how much does it increment each time? So in this case, it increments always by 1. So it means like we start at 1 and then comes 2, 3, 4, and so on. And also this one needs to be not null because we want to use it as our primary key. Let's create this one. And now whenever we enter values, we don't need to specify our employee ID anymore. You see, we start with the department ID, which is the second column. The first one is now automatically handled by the database for us. So if I run this query, where you can imagine this first one here is the employee ID column, which we don't see and we don't need to specify. I run this, I have again 3 records, and now have a look what we have. Now we have the employee IDs 1, 2, and 3, and automatically this was done by the database. You see, I never specified the number 3 here somewhere. So now you might be curious to see what happens if we try to add this entry here. And now we cannot enter this value here because this employee ID column is now managed by the database and it does not allow us to override this behavior. So in the end, that's perfect what we want. All right, the next thing I want to show you is that we can have global unique identifier columns. We already saw this new ID function before. And you remember this generates us a unique global unique identifier. And we can also use it to generate new IDs for our tables, and then they are of the type unique identifier, and we can use them as primary key. Running this, I create this table, and now I can go ahead and insert values into this table, and we created now an entry with this globally unique identifier. So when would you use one over the other? When would you use the identity or the GUID method? Well, it depends on your requirements. This one here obviously takes a lot more space than to store a simple number. But this one has the advantage of being unique. So whenever you have distributed systems, when one system generates a new entry and the other one at the same time, more or less, and then afterwards they need to somehow merge their data together, then you can use GUIDs to always be able to identify one row. Because with the identifier, they might add the same value at the same time, and then you have the same ID for the same record, which is not allowed for a primary key. So most of the time you would typically use an identifier column, but if you have the requirement, you need to know that this one is also available. While a primary key is always unique, you can per table only have one primary key which identifies uniquely your rows. If you have the requirement to have multiple columns where you want to enforce uniqueness, you can additionally create a unique constraint. If you want to create a table with a unique constraint, you can run something like this. You want to create a table in your schema with a name, and then you have a column here. Let's say in this case it's an integer column, and in here you can set a constraint with a name. Typically you would start this name with UQ for unique, but that's up to you. And then we have here the important part, unique, and then the column or columns that you want to enforce uniqueness on. All right, let's run this one. We have created the table, and now let's try to insert twice the same value. So if you remember, we have an insert into dev.testUnique. In which column do we want? We want in the unique col, and then we can specify the values or make a select. Let's select 1. It works. And if I run it now a second time, I get an error. This is a violation of our unique key constraint. So that's exactly what we want, right? We have enforced the uniqueness of values in this column. Now let's have a look at foreign keys and how we can implement them. The default setting for a foreign key is that it restricts changes on the parent table, so the one that it's referencing to, if there are records referenced from the child tables. So if you want to delete, for example, a row in the parent table, there cannot exist any rows referencing that row in a child table. Otherwise, we would have an invalid relation between those two tables. But we can also override this standard behavior. So let's have a look at our two operations that we have. First one is the onDelete. So whenever we want to delete a row. The default setting, as just talked about, is that nothing happens. We just refuse the deletion in a parent table if there are still records referencing that row from the child table. We can also set it to cascade. So when we try to delete a row in the parent table, all rows in the child table will also be deleted. The next option we have is to set them to null in the child table. So imagine we remove a row in the parent table, and then all the rows in the child table are getting a null value in the referencing column. Or the fourth option is to set them to their default value, the ones in the child table. And the second operation we have is updating. So on update, whenever we try to update a row in the parent table, default again is nothing happens. Or we could set it to cascade. So imagine you update an ID from a 1 to a 2, then all the ones in the child table would also be updated to a 2. Again, we could set them to null or set them to the default value. Now let's go ahead and add a foreign key to our existing employee table. The constraint shall have the following name, and it's on our zip column. And we are referencing the zip table, also on the column called zip. If I run this, I get an error indicating that the types of those two columns are not the same, which is true. And we would have to change our column. If you remember, in our zip table, the zip column is a small int, and in the employee table, the zip column is a varchar 10, which is not compatible. So let's go ahead and change that. We want to alter our table def.employee, and then we want to alter within this table the column called zip to a small int. Worked. Now let's try to run this one again. And again, we get an error. In this case, we would be generating a foreign key violation. Why is it? Let's have a look at those two tables. As you can see, we have the zip entries in our employee table, but they are not present yet in our zip table. So we cannot reference them because they don't exist. We need to create them. So let's do that. All right, after having entered those values, now we can reference them. If I run the query again to generate the foreign key, now it completed. Then let's have a look how we can work with our foreign key in action. Let's try to delete a row from our def.zip, so from our parent table in this foreign key relation, where zip equals to 10,001. Running this, now I get an error. This is our default action where we refuse to perform deletes where they are still referenced from the child table, in our case from the employee table. The next thing we could try to do would be an update. If I try to run this, again I get an error. I cannot update this ID because it is still in use. All right, let's drop this foreign key again and recreate it with the cascade option. So it's the same, but now instead of the default values, we say on update, you shall cascade, and on delete, you shall cascade. Now we will try to run the delete again. Running this, it worked. So what happened now? Let's have a look at our tables. We deleted now the zip with 10,001 in the zip table, but it's also deleted in the employee table. Let's quickly restore those values. Now let's have a look at our table again, and we have our data back. So this is how you can work with foreign keys and setting those 4 different types of way to work with it. For remembering, we have no action, which we saw first. We have cascade, which we saw now. Then there's also set it to null. So in this case, if we would have a foreign key on our zip column, which sets to null, you can imagine if we delete this row with the 10,001, you would get a null here and here. And the fourth option would be if we delete this row over here and here, you would get the default value if there's one specified. Otherwise, it would be blocked. The last type of constraints that I want to show you are check constraints. And with check constraints, you can implement your own custom rules, so to say. For example, if we create a check test table quickly with a title column, which is a varchar and not null, and then we add a constraint of the type check. We give it a name, and in here we say the length of the title shall be bigger than 3. So let's run this, and then we try to insert our first value in here, first test. Running this works perfectly. First test has a length more than 3. Now, if we would add something that is only, for example, 2 characters long, if I run this, I get an error message stating that it's conflicting our check constraint with this name here. So this does exactly what we want, right? In this case, we said we only want where the length is bigger than 3. So this one is getting refused. And you can imagine everything that gets evaluated to a Boolean value, true or false, will be working here as our check constraint. Very powerful tool if you have custom rules where you need to specify the exact type of data that you accept in your database. Now let's have a look at temporary and temporal tables. Sounds very similar, but it's indeed quite a different thing. Temporary tables are used to store intermediary results, right? You query something, put it into a temporary table, and you can later reference this data. And on the other hand, temporal tables are used to store versions of your records in point of time, and then you can later go back and see how a record was in the past. You remember how we used common table expressions to split a bigger query into smaller parts. With temporary tables, you can take it even one level further. Let's have a look at how this works. So let's just select from sales.invoice lines. Normal query right here. And the same way we insert into tables, we can also insert into temporary tables. So we have to call them with the hash at the beginning. This is indicating now follows a temp table. And let's call this one my temp table. So I can run this. Now I just see the number of affected rows, but later I can query this table just as it is a normal table. Select all from my temp table. And here we go, the same result. And if I go ahead now and open the second window and try to do exactly the same, you will see that's not working. If I try to run this, it's not a valid object name. So this means every connection to your database server has its own temporary tables. So you cannot query temporary tables of your coworker, for example, or even as you see here in different tabs, you cannot reference the same name. Just as with normal tables, we can drop our temporary tables. And we often use this if we want to reuse a table. Let's say this time we are only interested in invoice ID 1. So we can have it in here. And maybe next time we drop this again, and now we want to do something with the ID number 2. I know it's a fabricated example, but you can imagine if you have bigger queries, it might make sense to split the tasks into individual ones. Now let's have a look at temporal tables. That's a different beast. So first of all, let me create a new table in here. We call it employee temporal. It's just a name. And it has a primary key, which is needed for a temporal table. We have some columns, like our last time we have the employee table. And now we have a valid from and a valid to column. Both are date time 2 columns. And here comes the special part, generated always as row start, not null, or as row end. So these 2 columns indicate from when until when the record in here is valid. And then we have period for system time. Here we define, okay, those are our 2 columns that we are using now. I know it's a little confusing, the syntax, but in the end it's always the same. You just can copy paste it from the script, for example. And then another thing that we need to say is with system versioning, so generate always a version from this table, on. And the history table, we need to give it a different name. In this case, we call it the same name, history, but we are free to give it a different name. All right, let's generate this one. And let's have a look what we have in those two tables. For now, nothing, but we have two tables now already. And now let's go ahead and insert the same data as we had in our normal employee table. Works just as fine. Let's have a look how our both tables look like. In the employee temporal table, we have our normal data, but also valid from and valid to, like the date time right now when I'm creating this record. And nothing is in the temporal history table. Now let's go ahead and change our history a little bit. Let's make an update. So employee number 1 gets a salary raise. Running this works perfect. And now let's have a look at our two tables here. We see now we have again 3 records in the first table, but this one got updated. And the timestamp changed. As you see, it's like half a minute later. And down here, we have now one entry in the history, which is valid until the next one is valid from. And here we have the old one. So there you get it automatically having a history on your table. Very powerful for auditability, for example, or if you really have another use case where you always want to track history of your data and don't really worry about managing all this. It happens in the background automatically. Next up, we will be looking at views. Views are used to store predefined queries for later reuse, that you can easily give them this query a name, and then you can always just query the view instead of always rewriting bigger queries. Let's say we have a query like this, where we query our employee data and take the city from the zip code. I can run this, and here we have the columns of the table E, the employee table, and from the Z table, we get the city column. So this is something that we might want to query very often. And if that's the case, or maybe we want to store this query for our coworkers to also execute easily, we can create a view from it. We say create view dev.view employee maybe as, and then comes the definition of the query. And that's it already. If I run this, I have created this view, and now I can use this like I query a table. Select all from this view. If I run this, we see I get the same results, including the city column from the zip table. If I want to change an existing view, I would use the alter view. As you can see, in SQL, we often have repeating patterns. Like before, we had alter table. Now we have alter view to change an existing view. So what's the name? We called it dev.view employee. And then we say as, and now we have a new query here. Maybe we just don't want these technical columns in front, and we want the salary in K. I can just run this and then select the data, and there we have the updated view result. When defining the content of our views, we can use the normal SQL that we know for now. So for example, we can say where z.zip equals to 10,001. Can run this and then select from the table, and as you can see, works perfectly fine. What we cannot do though is to add an order in here. So I cannot say order by salary in K, for example. If I try to run this, I get an error message, because in views we cannot add order by clauses. And the reason is that it does not make much sense to put it in here, because you can imagine you query them like tables, and then you would have maybe a join from view A to view B. And what would the ordering then be? So if we want to order the results, we have to do it outside. We can order our query results as usual. In this chapter, we will be looking at procedural control flow. So before we saw the case when statements, which is already similar, where we had a case statement and then when this happened, put out something. In this case, we will now look at if else. If you're familiar with programming, this is very similar. Then we also have cursors or while loops, where we continuously do something over and over again until a specific condition is met. First of all, let's start with a simple if-else logic. So say you have the following query, which returns us the day of the week. In this case, it's a Friday. Now we can say, for example, if whatever the result here is equal to Friday, then we do something. Let's say we select, thank God it's Friday, TGIF. If I run this, I get TGIF. I can also say else, which is then the otherwise case. We could say in the else case, we select not Friday. If I run this, obviously the day did not get changed, so it's still TGIF. If you remember, the case when statements look pretty similar, right? I could just rewrite it like something like this. Case when Friday equals to whatever weekday we have right now, then TGIF, else not Friday. I run this, I get the same result. But what I can do with if and else is to do totally different things depending on the outcome. So with the case when, I am already in a select context, and then I add another column with the case when. With the if and else statements, I can do whatever I want. So I could do something totally different here. Maybe I want to select the max salary from dev employee for whatever reason. Or I could go ahead and call different stored procedures over here, for example, which we are going to see in a moment what that is. So in general, with if else, you are like outside of a select context, so you can do whatever you want. With the case when, you are already inside a select and you want to just add a column in here. That's more or less a big difference between them. Next up, let's have a look at variables. So for example, I can declare a variable with the name @myvar. They are always starting with an the variables of a type int. And then I can later select the value of it. If I run this, I get a null because we did not put any value in there. How do we do it? So what we can do is in between here, we set our variable. myvar equals to, for example, 10. If I run this, I get a 10. Another way to set my variables is to do it directly on the definition where we declare our variable. I can say my var of type int equals to 20. Running this works perfect. And last but not least, we can set our variables based on results of selects. And this comes in handy when you, for example, imagine on Fridays, I want to do something. So you can put a variable there that you can later use. How you can use them later, I will show you in a moment. But for now, let's say I selected here as 15. So first I initiate it with 20, then I reselect it, and as last step, I will select it. And as you would expect, we have finally the 15 in here. And instead of hard coding our values here, we can, for example, say select the top one salary from our employees. Let I run it alone. It's 120,000, and I can also put it in here in the variable. And the variable is also then 120,000. But what I cannot do is get back here more than one value, right? Because this is just one integer. So I cannot put in here two integers. If I try this, let's see the result, 120,000 and a null. If I try to run this now into a variable, I will get an error because this subquery returned more than one value. So if you encounter the error, this is what it means. You have a variable that can only hold one value. And now it's quite easy to imagine how we can combine those if and else statements, right? So let's say we have this part here, and then instead of selecting it, we can say if my var is bigger than, let's say, 100,000. And then I can also add begin and end. This is just optional, but just so you saw it once. And in here is then what I do when it's bigger than 100,000. Let's say good. And then we have maybe an else case, again with begin and end. This is becoming mandatory, the begin and end, if you have multiple statements in here, which is also possible. Well, and then maybe we say needs salary raise, right? For this works perfectly fine. As remember, it was 100,000. Oh, I put it here as 10,000, but with 100,000 it will be just the same. But what if you really want to store more than one value in a variable? Well, you could go ahead and make it in varchar value instead of an int, and then comma separate, maybe put in your values there, but that's not very elegant. You can also have table variables. So I can, as we saw before how we declare our tables, we can also put an at in front, and then it's a variable. So we can have a table with 2 columns, and then we can select from this table. Now, if you remember how we get values in our tables, we do an insert into the table, specify the columns, and then put in some values here. And now we can run this all in conjunction. And we see, okay, we have defined our table variable and it has the content of those inserts. Now let's have a look at loops. For example, we have a while loop. And here we have while 1 is smaller than 2. Select 1 is smaller than 2 as the text. If I run this, I will create an endless loop. And I have to stop this now. So this is something we obviously don't want. So let's use maybe a variable for this. We can declare a variable that we might call at counter of type in, which shall start at 0. And then we say instead of smaller than 2, we say begin and end. So in here we have multiple instructions. So we can say select the current value of counter. And also we set at counter equals to at counter plus 1. If I run this, we see we have now a 0, a 1, a 2, and so on until 19, because 19 is the last one that is smaller than 20. Once it switches to 20, the loop stops. And I can also break out of my loops with the break keyword. So let's say, for example, we make another condition in here. If our counter is equal to 3, then we do something, and what we do is break. Break means to stop the current run of our looping and continue with the script after the loop if there's something else. So if I run this, now we only get 0 to 3, because once we arrived at 3, we go into the break and the looping ends. Besides the while loops, there are also cursors, and cursors iterate over a table row by row. If I paste in here a simple cursor, you can already see that this one is rather complex. And most of the time I prefer to use while loops because, yeah, cursors are a little bit complicated, but it's in the end, it's just copy paste the logic. But in the end, it's just most of the time copy paste existing logic. So you can just Google or take it from the script. Anyway, let's have a look at what we have here. First of all, we declare a normal variable. We already know that. And then we declare a cursor named order cursor for, and now follows a select. Let's have a small little peek in here. This is just the order IDs from the orders table. Okay, so we declare our cursor for this table. So we have here 73,595 rows that we are iterating over. And then we need to open our cursor, and then we will fetch the next row from our cursor. So in this case, as we never fetch something, we fetch the first row, and then we run this cursor as long as the fetch status is equal to 0, which means I still had a row that I could fetch. So if we are over the 73,595 rows, the fetch status will switch to something that is not 0. All right. Then we begin our looping, we do a print of maybe our order ID in this case, and then we fetch the next row into our current variable. This runs then for all the rows that we have in here. And finally, once everything is finished, we need to close our cursor and deallocate it so the memory is released again from the database server. Let's run this. And there we have it. We have now an output where we were putting out all the order IDs for every row. And this is what you do typically with cursors, right? You go from row 1 to the end of the table. And if that's your use case, you can also declare it as a fast forward cursor, which means it just runs faster because it knows I can only go ahead. Because with cursors, if you don't have them fast forward, you can also go back to the previous row, for example. But this is typically not what you want. And if you want to know how to do that, go ahead and Google it, but I never needed it. So I always declare mine as fast forward because I know I want to go through all of the records. If I run this, instead of 1 second, now it runs in 0 seconds. Obviously, this might just be affected of other processes that are running on my PC right now, and 1 second versus 0 seconds is not really statistically relevant, but it is faster. Now let's have a look at dynamic SQL. Dynamic SQL is like your last resort if I'm not getting the goals with normal SQL queries and I need to be super dynamic, and maybe a report has logics where you want if it's going route A, it does something totally different than route B. So use it sparingly, but it exists and I want to show you what it is. So I call a variable dynamic SQL and it's just a big old varchar. And then in here I can set queries, but I write them out like text, as you see. And then there's an exec command where I execute my dynamic SQL. If I run this, I get the results from the def.employee table. Works fine. Next up, we will be looking at functions. Functions are similar to views, but you can also give them parameters. And yeah, in the details, you will see that there are quite a few differences between those two. We had used functions already before, like this one, the upper function. If I run this, you remember we make the test in small letters to uppercase, big letters. So this is a scalar function. It takes several arguments and then returns exactly one value. And we can also define our own functions. For example, like this. We have the create function, and then in our schema, we give it a name, and then the parameters that we are going to give it. So in this case, a quantity of type int, and then the unit price of type decimal. And then this one returns a decimal. And now comes the definition. Between begin and end, we have our calculation here. We return the quantity times unit price. When I run this, we have successfully created our own function and we can now use it. For example, like this. Select from our function, like with the built-in ones, it's the upper function, and now it's the function get revenue, and we give it a 10 and a 150, which correlate to our quantity and the unit price. We can run this and we get a 15. So this is then the product of quantity times unit price. So you see, this is the benefit of functions, right? You have reusable logic. Obviously, this is a rather simple function, but you can imagine them to get much more complicated, and you only have to write it once and then you can reuse it later. Obviously, like with the built-in functions, you can also use them with queries based on returned rows. So for example, this one, we have a quantity, we have a unit price, and then in here we have our as third column f get revenue function where we give it those two columns, quantity and unit price, and in the result we have the calculation, like if we would multiply them directly. Next up, we have inline table valued functions. In contrast to scalar functions that we saw before, they return whole tables, so not just one value. And in this case, we have a function get high paid employees, which take a salary, and then we return a table. And here we have a select. Give me all the employees with a salary bigger than the parameter that we gave it. We can run this to create the function. And then when we want to use it, we can say select star from dev.f get high paid employees, and let's say everybody over 100,000. If I run this, I get all the employees with a salary bigger or equal to 100,000. As you see, now we are returning a whole table and we can select from this table. So in this case, now it works really as a table in our query. Next up, we have multi-statement table functions. In contrast to the inline table valued functions, they allow us to have multiple steps of calculations based on an intermediary table that we can create. Let's have a look how this looks like. So we create a function, normal create function, give it a name, a parameter, And now this one returns a table variable with defined columns, first name, last name, and salary. And then the calculation logic begins after the begin statement. And in here we insert into our newly created table variable with those columns a result of a select query. And then later we return over here. And with the multi-statement table functions, we could also go ahead and do something later in between here, right? We could update our add my table. But finally, this is the table that is returned. So let's create it. And now, again, we can query it. Same result as before. So in general, you should try to avoid those multi-statement table functions, as they are performance-wise most of the time worse than the inline table valued functions. But if you need this functionality to have an intermediary result that you want to update or do something else with it later within the function, then they are the ones to go for. Now we will be looking at pivot and unpivot. Those two are used to move rows to columns or columns to rows. And we will have a look at how this is implemented. So yes, we use pivot and unpivot to change columns and rows of our result sets. They work similar like pivot tables in Excel. So let's say you have a table where you have a year, month, and revenue. Then you can perform a pivot and you end up with a result where you have pivoted the months into columns instead of rows. The value of January 2020 will be in this column. The opposite operation is called unpivot. Let me show you an example. I have here a rather complex query, and as you see, we have one comma table expression and then a final select that selects from this comma table expression and finally does a pivot over some columns. All right, so let's first of all look at the data that we are dealing with. We have the full names of our salespeople, and the revenue is in the second column. That's the sum over the quantity times unit price, all grouped by our name for the seller. So we see Amy Treffel has here something, I don't know what is it, 17 million and something revenue generated over all time. All right, now we can use the pivot to transfer all this together into columns. And this is the result of the whole query, where we took the initial result and then we performed a pivot. First of all, we need to add here an aggregation function. In this case, we want the sum of the revenue. This is in the end what you will get up in the cells in the final results. And then we say for the full name in, and then a hard-coded list of the name of the salespeople we have here. These are the names that then will be put into columns in our final result set. Now let's add another column, the year of our O.order date as order year. And this is now a second column that we have here in our query. So we also have to group by this column. Let's see the data that we are going to work with. Now we have the full name, then the order name, and then the revenue. As you can see, we have multiple entries per full name. All right, now let's see the result of the full query. All right, now we have it also with a column order year over here. So as you see, we have never specified the order date in our pivot statement, which means everything that is not part of our for definition that we want to create columns for, nor is it part of our aggregation, then it's like in a group by manner used, right? You have it like group by the order here, the result set over here. And then we could go ahead and also order it by our order year. And then we have a nice data set where we have pivoted our salespersons. Now let's store this result set into a temp table called pivoted, which we can later use as a source for our unpivot example. And now from this temp table, we can write an unpivot query. So inside of it, we have our names of our salespersons. So we really have to name them the way they are called in our base data set. And then from this source, we say we want to perform an unpivot, and we want to get the revenue for the salesperson in the list of those names over here. And finally, we want the salesperson and the respective revenue in the rows. Let's run this. And now we have a data set where the salesperson is in the salesperson column instead of as individual columns. Next up, we will be looking at window functions. A window function is something like, if you imagine you have many rows and then you define a specific window over all your rows that you want to calculate something on, and it goes through rolling through the table. A very powerful tool to have complex calculations directly in your database. So we use the window calculations to calculate data over sliding windows. What does it mean? Let's say we have this data set, and now we want to add a column, revenue rolling sum. When we do that, we want to calculate in the first row 1000, right? There's nothing before the January of 2019, so it should be 1000. Then in the second row, we want to have the current value plus the previous value. In this case would be 2000. And then the next one would be 1000 plus the previous 2000, which means 3000, and so on, right? This is what you can do with window calculations. Another thing that you can calculate would be, for example, revenue year to date, where you have the same logic within 1 year, but once there's a year switch, we start again from the first row, in this case 1000 in year 2020, right? First, let's generate a temporary table with some data. I will just run this, and then we see finally we have a temporary table with 3 columns. And then the measure is the sales that we are interested in now. All right, let's add a window calculation then here. First of all, we have our columns, full name, order, date, year, and sales. And then we add a window calculation. And it looks as follows. We have an aggregate function, in this case a sum over our sales. And then we say we calculate it over a window. So this over indicates now is following a window calculation, and the window that we are calculating over is just ordering our whole data set by the order date year, so by this column, and then we give it a name, running sum over year. Let's see the result of this. And now we see for 2013 we have this value. It goes until row number 8 in this case, and then 2014 has a different value. So for now it looks quite sparse because we were aggregating over the full name in this case. Now let's go ahead and add another window calculation column here. In this case, we will also put in the full name as an ordering criteria, and we call this running sum over year and full name. And when I run this query, we now see immediately that there is some rolling sum going on, right? In the first row, we have 4.6 million, which we also see over here. But then in the second row, we have the sum of those two values, which is then equal to this 9.3 million. Obviously, we could have gotten to the same value here if we were making a group by aggregate function, right? We could run a query which selects the sum of sales revenue over the sales data set grouped by order, date, year, and full name. But we would lose the columns over here, because when we run a group by function, we always group our rows together. And with the window function, that's the big difference. We keep all our rows and just add more columns to the result set. As you might expect, we could just use all our aggregate functions that we know now. So instead of running sum, we could also calculate a running average. Easier said. For now, our window was simply an order by, so an ordered window that we calculate over. But we can also have a different type of window, which is partitioning our data set. So in this case, we calculate the sum of sales over the window, which is first partitioned by the full name, and within each partition, it's ordered by the date and year. Let's have a look at the result of this one. Now it looks different, right? Now we are calculating over the full name. So in this case, Amy Trefel is our partitioning column. And within this partition, we order the data set by date, and then we make the sum. So here we have in the first row, obviously it's 1-to-1 the same value. But in the second one, we see then it's the sum within the partition Amy Trefel, who is our salesperson in this case. And then we could also go ahead and maybe divide this by the total sales of Amy Trefel. You see, now without the order by, we have the full value. Before running this, let me actually show you the result. Now we see the last value in this column, right? This is a sum over the whole set of Amy Trefel. And now we could, for example, go ahead and divide those. And then we arrive at like a percentage value, right? In the first year, Amy was doing 27%, and then the first and second year together are 56% of her sales, and so on. Now I want to show you rows and range, which we will be using on a different data set. So first of all, let me generate another temporary table, and let's have a look at what we are dealing with. So in this case, we have 4 columns. We have again the full name, the order date, in this case also the months, and then the sales. So we just added the months in between, because with this I can show you the rows and range keywords better. Let me paste the following in here. And first we have a window calculation over the normal running sum, as we knew it before. Also added the month in here, but this is what we had. And then we have another window calculation ordered by the same columns, but we add a range unbounded preceding. Let's have a look what this does. Running this, we see the results look the same, and indeed that's exactly what they are. So the default value is unbounded preceding and current row. But what happens if I change that? So for example, I could calculate over rows between the current row and the current row. So now my window, I'm shrinking it to only the row that I'm looking at. If I run this, I get 1-to-1 the same value for every row, because the window for this calculation is now only the current row. So I could maybe say, instead of unbounded preceding and current row, we can say between current row and unbounded following. So now I'm turning around the window. If I run this, we don't really see the effect for now, because we did not really order our data set. So let's order by full name, order date year, and order date month. And now we see the order of those calculations is inverted, right? In the first running sum, it's always rising, and in the second one is always falling. If I go all the way down to the last entry of Amy Trefel, we will find this running sum in this column. Let's go down here, and there it is. So with this one, I am inverting it. So you can play around with the rows that you want, but it's not always unbounded following. I could also specify the number of rows that I want to have following. So for example, the 2 following rows. If I run this, we see a different result. Now, this value is the sum of all these values. So it's the current row plus the 2 following. So these 3 together are now this value. So you see, with the window functions, you can precisely calculate over windows that you can define yourself however you want to mix and match these logics. Now you might wonder why I once switched from range to rows. Well, they behave very similar, but if you have same value in the result set, then range will include all the following rows which have the same value. So in practice, I never really needed it, and I always go for rows, which is for me easier to understand what's going on. I can exactly see where my window is. I don't need to look at the data to judge which entries are part of my window. but so you know, range also exists and includes the same values in contrast to rows, which really just looks at the number of rows following and preceding. Now let's say you have the following definition. You have a sum and an average. You can easily run this one. And we see that we have common parts in here, right? The window definition is the same. And whenever you have that and you don't want to repeat yourself always, like with 2 times the same, it's probably okay to do it like this. But imagine you have 10 times the same window that you want to calculate over. Then you can also use the window definition. So I can go ahead and say window, and I give it a name W as, and then in parentheses follows my definition of my window. In this case, the partition by full name, order by order date. And then I can replace those 2 instances here with the W. And when I run this, the result stays the same, but the query looks a little bit cleaner. I have the window definition only in one place. Over Windows, we can use all the aggregation functions that we know, but there are also special ones only available for the window functions. For example, we have the lead and lag functions. And to see the result better, let's also add in our order by the order date months in our window. And when I run this, we can see the effect, right? Lead is always leading now 1 row ahead. So the value that I show here is the one from the leading row, 1 row ahead. Here, it's also 1 row ahead. And lag does exactly the opposite, right? The first one is null because there is nothing before. But then on the second row, we show the value of the first row. So these lead and lag are like a shortcut to a rows specification where we say 1 row preceding or 1 row following and the current row. Next up, we have the first value and last value. If I run this, we always get now the first result in here, everywhere the same, it's always the first row. But then with the last value, it looks a little bit strange, right? We would expect to get the last value of Emil Trefel, but this is not how the last value works. Most of them use the standard window behavior, and it's again the unbounded preceding, so all the rows preceding, and current row. So the last result looks only up until the current row. So this is always the last value that it sees. So most of the time, this is not what we would want. So we would want probably to add a rows definition between unbounded preceding and unbounded following, right? If I run this, we see the result that we would expect. The last value of Emil Trefel is then probably this 5 something. If I scroll down here to the last value of Emil Trefel, there we have it. Now it works as expected. So this is a little bit of a trap when you use the last value, because whenever you work with these window functions, try it out and you see the result, but have in mind, it's always the unbounded preceding and current row if you don't override this definition. Next up, let's have a look at row number and rank. So first of all, let me clean up here a little bit. And then we have row number over order by, let's say, those 2. And then we have a rank over the same. And when I run this, we get some orders in here. So the number of records. If I scroll down here, you see this is a number that's then always incrementing for each row. The difference between row number and rank would be, again, if we have a tie. The row number really counts the number of rows, and rank counts the rank number within. So if we would have a same value in here, the rank would then skip 1, so to say. But most of the time they give us the same result, and in practice, most of the time we are interested in the row number of a record. But so you know, rank also exists, and the difference is that it accounts for tight places in the dataset. Let's have a look now at stored procedures. Stored procedures are very similar to functions, but they are more powerful and a little more complicated to use and serve a different purpose. And you will see it in this chapter, why we have them and what to use them for. To create a new stored procedure, we will run the command create procedure. We will give it a name, and then the rest looks pretty much as we saw it before with the multi-step functions. In this case, we give it a parameter, and then between begin and end, we declare something that shall happen. In this case, we declare a table variable, we insert into it, and finally select it. So let's run this. And now we can execute our stored procedure by specifying exec, the name of the stored procedure, and then the parameters followed after here without parentheses and comma separated if we have multiple. There we have it. And if you understood the functions, stored procedures are pretty much working the same way, except for that we execute them instead of selecting from them. And within the body of a stored procedure, you can do whatever you want. You can create new database objects like tables or views. You can call other stored procedures and pretty much do everything that you want inside there. Whereas functions are a little bit limited, right? They are just used for selecting data. But what we cannot easily do with stored procedures is selecting from them, right? If I try to say select everything from the result of this stored procedure, this will not work. And there is a workaround to circumvent this limitation, which is most of the time not what you would want to do. If you just want to select from a multi-step thing, use functions. But if you really need to, let's redefine our function a little bit. So we give it the same name. We say alter procedure to alter it. And then we will work with our return type. So if salary is less than 0, maybe that does not make much sense, and we return a 1, like a status indication. Did run onto a mistake. And then we have again our table variable. We insert into it. We run the select that shall be inserted, and we select from it. Now it's created. And now we had like a return type, right? And let's use this. So now we can declare a return type of the type int, and we execute our stored procedure with the same value. In this case, I'm specifying exactly its salary shall be 100,000, but you could just as well leave it with 100,000 without specifying the name of the variable. But we define a value with the returned value of this one. So let's see what happens. Now again, I'm returned my dataset, but I get also a value back. In this case, it's 0. And you saw we said if smaller than 0, return a 1. So let's try what happens. Now I returned a 1 instead. So there's like an indirect way to get the procedure to return something. So we add another parameter, we call it max salary, and we specify it as output. Now we can set this value. So in this case, we will maybe continue to return a 1, but finally, after the select is done, we will want to say set our value to max of salary from our table value. Now I will alter this function. It's missing a select. And then let's see what happens. So we need to specify also here the parameter. Let's give it a name, max salary. And this one shall be max salary output, where we will be storing our value as an output variable in this case. And then afterwards, let's select max salary output. If I run this, I get back a -1. But if I say, give me all the salaries bigger than, let's say, 10,000, if I run this, I still don't get the value because I also need one additional step to define this one also as output. Now, when I run this, finally we have our output value. You saw it took a little bit of steps and finally it worked, but you saw it's just possible, but in practice, try to avoid using this functionality. Now we will be looking at triggers. Triggers are something that fire on a database when something happens. For example, a row is inserted and then a trigger fires on this row insert and does something. Maybe check some calculations or does some logging. In general, it's refrained nowadays more or less from using triggers, but it's good to know for you what they are and to spot when there's a trigger involved and when you don't understand why something is happening in the background maybe. Let's create our first trigger. To do that, we run a create trigger. We give it a name on a table, and then it shall trigger after something is inserted in this case. You could also make it update or delete, whatever you need. And then you say, for example, print something. But here you could obviously do whatever you want. Any T-SQL that you can run here is something possible. So you could, as I said before, run, for example, a logging of something that happened. Anyway, let's create this one. And then let's insert a row into this table and see what happens. And now after inserting, the first thing that we see is our print something happened. So the trigger fired after this insert and did a thing. And as I said before, you could do pretty much everything that you want, but it's a little bit hidden, right? If you don't know that this trigger exists and you run a normal insert, you would not expect some side effects to happen. So triggers are prone to have undesired side effects if you are not aware what's happening there. If you want to get rid of a trigger, you would run drop trigger, as we did it with all our things before, drop table, drop view, and so on. It's always the same. And now let's try a delete trigger. Now when I run this trigger, there is nothing firing, right? Because it would only fire on delete. So let's delete this one. If you remember, we can run delete from dev.employee, where let's say our department ID. No, then we would delete all. Let's run it for where first name equals to my. So let's get rid of the ones that we just added here. Running this, we see that again the trigger fired, in this case for the delete operation. And then one thing that's also very interesting is, let's drop this trigger again. And instead of printing something happened, we can run a select from deleted. So deleted is like a built-in functionality where you could have deleted, inserted, or updated. So in case we run delete, there will be something in this predefined deleted dataset. Let's create this trigger. First, let's add a value again, and then we will delete it again. Let's see what happened this time. All right, now we deleted this entry again, but this time we saw what we deleted. So this is also something that you can do. And this is also maybe something that you would want to log then. And you could also obviously add another column where you have the current date with the getDate function, for example. Then this is how you would end up building your logging. So you can exactly see what was deleted when, and every column that you have here is what you can see then later in the logs. Now we will be looking at transactions. Transactions are something where you want to group together two operations, where you want to define either those two operations both complete, or if one of them fails for some reason, they shall both fail. So you can roll back to a state previous. It's good if you imagine, for example, like sending money from one account to another. You only want to have this transaction stored on the database level if both worked, right? Here you subtract the amount and here you add it. You cannot just have the adding without the subtraction and vice versa. So this is what you use transactions for. All right, then let's see how transactions behave in the system. First of all, let's have a simple select everything from dev.employee. So this is in one of our connections in one of our tabs. Here we have our employees. And in the second tab, I will now start a transaction. So to start a transaction, we will run a begin transaction or begin tran, which is a short form for just the same. But let's go with transaction. And then after we have begun our transaction, we want to do an insert into our employee table, as we did many times now. And then let's see what happens. I run this. And if I go back in my other window where I have a different connection to the server and I run the select, no result is coming back. Why is it? Well, there's an open transaction running on this table right now and it's blocking the results. One thing we can do is, for example, we can run it with no log. And this instructs the server to look into what is right now on the database level, ignoring those logs. So what we perform now is a dirty read. So let's stop this run. And then we run it with no log. Now we get the result. And here we see our transaction. So it's already there, but we could not yet see it. Now let's see what happens if we afterwards on the second tab run a rollback transaction. Actually, before doing that, Let's also run the select on this tab where we still have the open transaction. If I run the select, here I get the results back and I don't need no log, because in this connection there is an open transaction, and after beginning the transaction, I can see what's going on there right now in the data. But now I will run my rollback transaction. Rollback says I want to remove all the changes that were like intermediary in the database since I began the last transaction. If I run this and look again at the table, it's gone. So it was intermediary in the table, but the transaction was never actually committed. It was never really approved to be committed. And when we roll back, our transaction is like nothing ever happened. And now if I go back to the second tab again and I run only the select without the no log, I see it as it was before. And once we performed the rollback, this transaction was not hanging open there anymore, and in a different tab or different connections, we could have again queried the table as normal. So working with transactions, you need to watch out a little bit to not block your database forever. But why would I want to do that? Yeah, as I said, between this begin transaction and a rollback or commit, I can do multiple things, right? So I can first insert into one table and then maybe do another update on another table. And only if both are finished and committed, this is then permanently stored to the database. Otherwise, it's still in this intermediary step where other people or other connections cannot yet see the data because it's not committed. This is the magic of the transaction, right? You can put multiple data manipulating operations together in one step, and either it works as a whole or it does not work at all. But yeah, let's just do the same thing again. We begin our transaction, and in this case we commit our transaction. So this time we approve the changes that were there lingering, and then we select from it, and there we have it. The new row is now permanently stored in the database as an approved record. Oftentimes you use transactions in combinations with try and catch statements. So this would, for example, look like this. We can begin try, and then we do something that will work, divide 1 by 1, then an end try, and if we catched an error, we will print error. Running this, we just get our result. But if I run something that will produce an error, so dividing 1 by 0, if I run this, I get no result. And in the messages, I can see there's an error that we printed here. So if we run into this case, we will run into a catch because there was an error, and we do whatever is defined here. So what we then, when we combine those things, often do would be, after beginning my try, I will say I will begin a transaction that shall do something. And I will maybe give it a name, my tran. And then let's select something that will work. And after doing that, we have a commit transaction, right? And maybe just to see what's going on, we will add another print here. Print committing. And in the catch case, so there was something wrong with our insert or our select or whatever we were doing there, we can then say if add tran count bigger than 0. So whenever you see something starting with an add, it's always like a system internal variable that we are querying here. And tran count, as said, gives us the number of open transactions. So when we open a transaction here with begin tran, but we never reach to commit, once we are here, it will still be open. So then we would begin to do something with this information. So if we are in this case, we could then say rollback transaction because something went wrong and we don't want to have it lingering open forever. And now we can also specify which transaction we want to roll back. So in this case, we would want to roll back the transaction with the name mytran that we defined up here. So if there are other transactions open, this would not affect them. So this makes sure we are not interfering with other transactions from other users that might be lingering around, because we only want to roll back the one that we opened up here. So let's run this. We get back a 1 and the message is committing because it worked. Now, as you can imagine, if we produce an error over here, we run this, we get back 0 results. And in this case, we had an error. And yeah, we don't see it for now, but believe me, or I can also show you that we will also roll back this transaction. So in this case, we do the roll back. Once again, running this query, we don't get a result, but we went into the path where the rollback happened. So this is a powerful combination with a try and catch, because you can make sure that transactions don't stay open forever, and you always close them either by committing or rolling back, but they will not stay open forever and block your system. In this chapter, we will be looking at performance monitoring. So in general, a database should be fast, and if you see some degradation there, you want a possibility to monitor what's going on, and this is exactly what we are going to look at in this chapter. The first thing that we can do to monitor our query performance is to add statistics to our queries. So first of all, we say set statistics time on, and then we run a select, and in the messages tab, we have now some time informations. For example, the execution time was 110 milliseconds in CPU time, and the total elapsed time was 861 milliseconds. Let's run a query with a join. This one took slightly longer, and here we see, okay, CPU time was 500 milliseconds and total time was 5150 milliseconds. So why is the difference? Well, if you have multiple CPUs and the query is parallelizable, you will have less CPU time and more elapsed time. But so this is what you get with the statistics time on. Now let's remove the time statistics again and switch for IO statistics. So let's set them on and do the same first query. And here we see that it now took 692 logical reads. So this is what you would mostly be interested in, because this is counting how often do you need to go to your hard drive of your server to get back the data. And then let's also run the more tasking query. And again, now we have multiple entries here. So first we are querying the order lines table. This is the second part of our join. Here we have 4,631 logical reads. Then we have a work table. This is what intermediary results are stored into when we do our joining. So in this case, that was not needed. And then we also query the orders table, the first one of our join. And here we have 692 logical reads. So, and if you optimize your queries, you often try to reduce the number of scans that you have to do. A scan is always an operation to scan over the whole table when there are no indexes available to help us. What an index is, I will show you in the next chapter. But for now, let's remember scans are something where I scan the whole table and I don't have any help from the data structures. And obviously, I will always try to reduce the logical reads where I, for example, add where conditions when I don't need some data. And if you reduce the reads, then you have less I/O and therefore faster queries and less load on your server. And then afterwards, let's remove the I/O statistics again. The next thing we can look at are client statistics. So these statistics we saw for now are all on the server running the queries. But as a user, for example, here in the SQL Server Management Studio, obviously also my PC has to do some work after receiving the data and to put it, for example, in my tables. And we can also see that. So let's run a query, but let's also include our client statistics. When I run this, I will now have a tab Client Statistics. So this is what my client had to do and what was going on here. For example, we received 73,595 rows. And this is in bytes what we received here. So you can see exactly how much data was transferred over to the client after running a query on the server. The next thing we can look at are execution plans. So let's include the actual execution plan. So this is how technically the server handled the query that we sent to it. Let's run it for the first simple select. Then I get an execution plan over here. And this one is quite simple. So first of all, I do a clustered index scan. So I'm scanning the whole table, and the actual object that I'm querying is the primary key of the orders table. Now let's look at how this looks when we run a query with a join. So now there's something more happening, and we typically read it from right to left. So on the right, we have the sources. The first source that we are querying is, again, the orders table on the primary key. And then we also query the order lines table also on its primary key. Makes sense, right? We want the data from the sales and the order lines table. And to perform a join then, there are different types of joins. In this case, it's a merge join. A merge join is joining the data ordered already together. And in order to have it already ordered, there is another order step added in here for the order lines. So we query the order lines, then we sort them by the order ID in ascending order. So we get the same order back as from the orders table. And then we join them based on our order ID. And finally, we return the data. Now we saw a merge join. Then there are also hash joins or nested loop joins. But in general, we leave this up to the server. The server decides how can I most performantly perform the actions that the user was asking from me via SQL. But I can also force the server to use a specific join type. Sometimes, very rarely, this is useful when the server just does not get it, especially when the queries are extremely complicated. Normally, we leave this up to the server because most of the time we are causing more harm than it does good. Just for some very edgy cases, it's good to know that these options exist. So this would have been an inner merge join. If I run it like this, we get the same execution plan. But I can also say I want a hash join. And let's see what happens. Now the execution plan looks a little different. You see there's no more sorting after receiving the order lines. This is because the hash join does not rely on pre-ordered data. It just generates hashes, in this case on the order ID, and then merges them together. A hash join is often very efficient if you join two big tables together. And then this one also needs a gathering step to bring together the individual hashes into one final data set again. And then we return it. And the last one would be to have a loop join. Let's have a look at this one. And again, we come to a different execution plan. The first one that we see is a scan on the orders. So we retrieve all the orders, but then we have an index seek on the order lines. So here we are picking individual rows that we are joining with a nested loop. So in this case, we take all the order IDs from here and then individually pick from the order lines. And then with the identified order line IDs, we also query the whole order lines table again, but individually we make a key lookup. This is then picking individual records from the order lines table as a whole, and again loops it together with an inner join and finally selects it. So the nested loop is very different, right? You have typically one big table and then you individually pick individual rows from a joint table that you then put together in a for loop. You can imagine that. So we have the merge join, which is the fastest, but this one relies on having already pre-ordered data sets. And sometimes ordering costs so much that it's not worth using the merge join. And if that's the case, we typically have a hash join scenario where you have two big tables that you want to join together, which are unordered. And then the loop join is typically something that the SQL server would decide to use if you have one big table and a small table that you loop to the records. So in general, all will always work, but it's a matter of which is the most performant to pick. As you see, it is a very complicated topic and you could spend many hours investigating your plans. But the joins are the most important part. besides the scans versus seeks, where we will use the indexes, which we see in a moment. But yeah, it's a complicated topic. And my recommendation would be, if you have unperformed queries, look at the execution plan and try to figure out what's happening, and then think about what should happen, and maybe you can nudge your queries in the right direction. Now that we know how to monitor our performance, the question arises, what can we do with this information? Well, most of the time, setting indexes will help speed up database queries. And in this chapter, we will be looking at indexes and performance in general. Now let's have a look at the arguably most important topic when it comes to query speed optimizing. Those are indexes, and they are a means to make fast data access to tables possible. And you can imagine them to be similar to indexes that you find at the end in many books, where you have some keywords and then you have the list on which page do you find it. This is more or less how indexes in SQL Server work, right? You have an index of data and it tells you in which part on the hard drive of this big, huge table you will find the data that you're interested in. On the disk, the data is actually stored in pages, like pages in a book, where you could say, okay, on page X, you will find this data, and then you have just to read one page instead of always the whole book, if you're only interested in a specific part of your whole book. Right? This is how the index in a book looks like. If you are interested in apples, you will go to page 57. And then in SQL Server, you have different types of indexes. The first one would be a clustered index, and a table can contain at most one clustered index. This one is typically reserved for the primary key, so you can very fast search for the primary key because the whole table is structured in this index, which is based on the primary key. So this is then the fastest way to search for the primary key values. And this one is then restructuring the whole data of the table, right? You don't have the index at the end of a book and then some text before, but it's more like a telephone book where you store all your data in an ordered fashion. And with this structure, you can seek through the whole book very fast because you know the letter start is the ordering criteria for the whole table. And this also makes clear why you can only have one clustered index, because the whole table is stored in this index structure. On the server, it's actually stored in a B+ tree on the disk, and it looks something like this, where you start on top on a tree and you see always, do I have to go left or right? Let's say we are interested in Frank Buschmann and we want to look in the B, obviously. So first decision is, are we between A and D or between E and F? In this case, B is between A and D, so we go left. And then we go into the second area where we have the B, and there we find Frank Buschmann. This depiction is a little bit simplified because in a real implementation there are reference pages in here, but to understand the concepts, this is what you need to know. And then there are also non-clustered indexes. And you can have as many non-clustered indexes as you want. And the non-clustered index is actually like the index at the end of a book that I first introduced, right? It's not like a telephone book, but it's the index at the end of the book. This one is also structured as a B+ tree, but in the leaves you don't find the actual data, but you find references to the actual data, which you can then look up, for example, in the clustered index, and there you will find the data. So it's taking one more step to get to the data when you have a non-clustered index. But as said before, you can only have one clustered index, so this one is like your fallback if you have two search criteria and you can only have one clustered index. And in our example before, we had ordered the clustered index by last name. This one does not help us if we want to search by first name. So here we can have another non-clustered index, which is based on the first name. And then you can go through the tree structure again, and at the end you will find the first names. And then in parentheses shown here is the reference to the clustered index. And this is then the key that you would go ahead again and search the other tree, which is then stored by last name to get your final records. All right, let's see this in action then. First of all, let's have a look at our execution plan when I run a query on our employee table. In this case, we did a clustered index seek. So we obviously already have a clustered index. And this is what we already implemented when we were adding our primary key to the database. So if you don't specify it other ways, whenever you do a primary key, you also immediately generate a clustered index based on the criteria of the primary key. In this case, the employee ID is our primary key. So we can have an efficient index seek. So it's seeking through the tree, as I showed you before. Now let's see what happens if I search for the first name Don, which is not part of the primary key. In this case, we have an index scan instead of an index seek. So in this case, I was really scanning the whole table to find the first name Don, which is not very efficient. As our table only has a few records, this is not much of a problem, but we can have it more efficient. Let's go ahead and create a non-clustered index on our first name column, right? This is the name of the index, on which table, which column. I will run this. And then I run this query again. And again, we have an index scan. Why is it? Well, the SQL server realized, okay, this table only has about 4 records. It's faster to read in all the records and just look for the first name Don in that result set instead of going through this double hop of index scanning. But if this table would have, let's say, maybe 10,000 rows, then there's like a threshold when the SQL server decides, okay, now that table scan would be so expensive, I will rather use the non-clustered index available. So you see, just because there is an index doesn't always mean the server will need it. But now it knows it has the option, and then with some heuristics and algorithms, it decides, will I use it or not? But if it would have used this one, we would have a plan which will first have an index seek on the non-clustered index with the name IXDEF employee first name. And then we will have a key lookup on the clustered index as shown before. But yeah, I cannot show it to you right now, but believe me, this is how it would work. All right, these were clustered and non-clustered indexes, and they are used to identify individual rows in our dataset. Then there are also column store indexes, which take the whole indexing upside down, right? Instead of identifying individual rows, they are used to index column-wise our database. And they give good performance if you are always querying big chunks of your data. And this is done by compressing the data in the columns. So you often use them for fact tables in a data warehouse where you query often many rows of individual columns. And even if you store your index in a column store, you can also add non-clustered indexes to identify individual rows to have the seek operations if you are interested in individual rows. So this one can be combined. In a row store, we store our data in individual rows that we want to identify. In a column store, we store our data in columns. And if we have a query like this, for example, select from sales the date and then the revenue, and then the sum of the revenue, all grouped by the date. If I would run this query on a row store, I will have to read the whole table to get the result. In a column store, I will only have to query the date column and the revenue column. I will not read the first name and last name at all. So this heavily reduces the I/O needed for the query because I'm not touching the first name and last name query in a column store at all. And then there's also compression, which helps us. So what's happening here? So the first step is value encoding, which I will show you only on the date column now. And here we have 2 different dates, and these columns are ordered in that row. And we have the date ID 1, which is generated, and this is the 1st of January of 2023. And then there's a second row, which translates to the 2nd of January of 2023. And then we can store just 1 and 2, and we have a translation table next to it, instead of always storing the 4 bytes of the date. So it's always just one value that we store, and they are then referenced accordingly. And then the second step is the compression. As you can see, we have first 2 rows with a 1 and then 3 rows with a 2. And then we can restructure our data as follows, right? The date ID 1, we have 2 rows, and then they are followed by 3 rows of the date ID 2. So this obviously relies on the order of all the columns. And then in the background, there are algorithms to find the best ordering over all the rows. So you get a very good compression, and it's all happening automatically in the background for you. But the downside of this compression is that it's a performance-heavy operation on the write time, right? You can read very fast, but writing has additional hoops to jump through. So this makes a lot of sense in a data warehousing context, where you have maybe in the night some loads, and in the day you have a lot of reads of your data, and you only write once. But this does not make much sense for an operational system where you have all the day reads because somebody is changing data and you have to reflect it in the database, and then you have to always run compressions. No, this is only valuable for a data warehousing type of queries where you have analytical queries and the data is written only once and then it's there. And then these groups are of around 1 million rows, but this is an implementation detail of the SQL Server. All right, let's implement one then. First of all, let's get some statistics on our sales orders. And here we see that, for example, we have the reserved size of 11 megabytes for this table. Let's copy this out to remember the values. And then we have some statistics when I run this query. So we had 692 logical reads and the elapsed time was 190 milliseconds for this query. Now we want to change this one to a column store index. When I try to generate this clustered column store index, I get the information that I cannot because there is already a clustered index on this table, which means we first have to drop this existing index on the primary key. And we are again not allowed to do that because there are foreign keys referencing this primary key and the index is needed to do so. So as you can see, we need to meet some requirements to actually use it, but let's remove them. So now we dropped all the foreign keys and then finally the primary key. Now we can try this again. Let's create this column store index. This time it worked. And now let's see at our statistics again. So before we had an data of 5 megabytes and an index size of 6 megabytes. Now we have data of 1.3 megabytes and an index size of 6.8 megabytes. And this is a very small table with just 73,000 rows. The bigger the tables, the closer they get to this 1 million, the more the compression will kick in. But still, we have less data, right? And then we have also our I/O statistics. And these are other things we were querying before this. Let's actually only run our query and then we see the statistics only for that operation. All right, here we have it. This time we had 0 logical reads and only 1 scan count instead of 692 logical reads. And then we had 1 segment read. So a segment is the equivalent for the column stores. So we were reading one of these segments. And then we can also see the elapsed time, which in this case was even worse than before. So in this case, for this table, adding the column store index in contrast to a row store index was even performing worse. So we should revert this experiment. But now we saw those 2 index types in action. So now, last but not least, let's look at some performance insights. So things that typically go wrong and things that you can look out for when you feel like your database is responding slower than it should be. So first of all, let's add our I/O statistics. And then we have a query with a where condition. And in this case, we got quite a lot of logical reads. It took 8 seconds. Now let's see what happens if we add an index to this invoice column. If I create this index and run the query again, we have just 86 logical reads and the query finishes in less than 1 second. So you see adding an index can definitely speed up your queries. But you should not come to the conclusion that in the future you will add indexes everywhere to every column, because every index needs also to have this tree structure, and this needs to be managed. Every time you write new data to a table where there's a non-clustered index, also this non-clustered index has to be reshaped potentially, depending on where you insert or delete or update in that index. So adding an index can oftentimes speed up read queries, but it will slow down write queries. So it's always a delicate balance, and you always need to check if the type of query is coming in so often that it makes sense to add the additional effort to maintain this index by the server. Obviously, you don't have to do it, but the server has to do it in the background, and it also takes its toll. Next up, let's look at search or search arguments. And these are important for the where conditions. Let's have a look at the following. I know that on the full name column of the people table, there is a non-clustered index. So when I run a full name like A, it should be rather fast. Let's see what happens. And indeed, we got a fast index seek operations. So we were seeking through the tree, starting with an A. But what happens if I put the wildcard to the beginning? Now suddenly the SQL server does not know how to traverse to the tree, because every leaf of the tree could end with an A and start with anything. So if I run it like this, suddenly we have an index scan, because now the whole table needed to be scanned. This is something to watch out for, right? You need to think about how your table is structured, which indexes are available, and how you can make use of them. Obviously, if you need to find every person that ends with an A, there's no way around. You will have to query it like this, but you need to be aware that there's a performance toll doing this. Another example would be the following. If I query the invoices date on the invoice column, this works perfectly fine. I get an index C on a non-clustered column because there's a non-clustered index on the invoice date. But what if I query it like this? I convert this date to a year, and then I compare it with 2016. I get an index scan. Well, why is that? I have a column with an index, but I do some kind of calculation around it. And this breaks the use of the index, because the SQL server does not really know what this does to our data. So whenever we query our columns and we know there's an index on it, we don't want this. We want to restructure our query so the index column is untouched. It's still searchable. Search arguments can be used on it. And I could write the same query in a different manner. I don't do any calculations on this column, because this column shall be 1-to-1 equal to the tree. And then I could say, for example, between 2016, 1-1, and then end of that year, right? The content is the same. Give me all the invoices from the whole year. But when I run this query, now I have an index seek, because these values are directly comparable to the content of the non-clustered key of the non-clustered index on this column. This is what we mean when we say our query is searchable. So this one is searchable, this one not. Sorting our results is one of the most expensive things that we can do in a query, even if it does not seem like that. But let's have a look. I will activate some time statistics, and then I will run a query, including a join, and I will run the same query, but add an order by. Let's run and see what happens. The first one took 234 milliseconds of CPU time. The second one was 391. The actual elapsed time was pretty similar. The first one even more, but this little bit based on what's happening on my PC in the background right now. But this is important, right? This one took much more CPU time than the first query, because this was adding an order by. And the message is, don't order your results unless you really need them ordered. It's always a performance impact. And this wraps up this video. If you have any questions, please feel free to leave them in the comments. I will try to get to them on time. Otherwise, if you want the video to go into one of the topics in more depth, please also consider commenting accordingly, and I will see if I can do that for you.